Hi, good morning. Uno, dos, probando, probando. Uno, dos, tres, probando, probando, probando. Uno, dos, tres, uno, dos, tres, probando, probando, probando. Uno, dos, tres. Sí, sí. Probando, probando. Uno, dos, tres, probando. Uno, dos, tres. Uno, dos, uno, dos, uno, dos, uno, dos. Uno, dos, uno, dos, uno, dos, uno, dos, tres, probando, probando. Vani, ¿me escuchas, Vani? Uno, dos, tres, probando, probando. Vani, ¿me avisas? El circuito tenía una salsa.
Dos, dos. Unos tres. Probando, 1, 2, 3. 2, 2.
Sí. Si ya tienes la capturadora aquí, sí. No necesitas, ¿no?
3, 1, 3. Hoy el delay está como más.
Sí, sí. Pero...
Bueno, pueden esperar que es el de YouTube.
Sí.
Yo lo estaba escuchando ahora por Zoom. No, pues está bien.
También en la escuela de que no hay luz en la escuela, me voy para la casa. Yo dije, espera que venga la luz. Sí. A los 5 minutos de que no va a venir. Allá la máquina. Están todos los papás y que los pasamos a buscar, que no sé qué. Ahí en la Salle. La gente piensa que también es parte del simulacro.
Así tiene conocimiento sobre en internet.
Ajá,
En algún momento fue al baño del hotel y se lo quitó y lo puso en una mesita y lo dejó ahí.
cuando uno está por fuera, uno tiene que salir con lo mínimo. Con lo mínimo.
Aló, sí, 1, 2.
You're going to share screen, yeah?
Yes.
Kind of give the be on the pointer, the plug. You're ready to go? Huh?
My name is
Well, name like that too. We are live. I don't know if my name is. Yeah.
Can actually change the frame zooming. You can change the zoom.
It's so cute.
Yes, ma'am. Yeah. I think you took care of it.
No, but sí, no. Es bien.
No,
No.
yeah, yes.
sessions. But if we think we can finish earlier,
Yeah.
maybe bring them early.
Muy buenos días a todos y todas y todes. ¿Cómo están? ¿Bien? Resolvimos bastante ayer, ¿no? Por lo que dijeron los colegas, las colegas. Bueno, iniciamos igual directamente, diría yo. Sachil, iniciamos el día, we start the day. Y creo que vamos a tener una sesión teórica primera. We are going to have a theory session first. Y desde ahí iniciamos a trabajar. Estamos también grabando y en vivo, ¿verdad? Porque tenemos la transmisión también en YouTube y tuvimos algunos participantes también ayer siguiéndonos en YouTube, así está súper. Ok, bueno, bienvenida. Le paso la palabra, el micrófono a Sachil. I'm going to hand over the mic to Sachil.
Thank you very much, Sabrina. Good morning, everyone. Hope you had a good night after a long session of R yesterday. Good morning, everyone, again. Does anyone has an issue about yesterday's session regarding anything that you haven't understood or you wanted to ask a question before we start today's session? Seems like everyone has understood, which is good. So we are still around, myself and my colleagues. So if you have any challenges in terms of downloading the data, the software, please reach out to us and we're happy to help. So for today's presentation, so I think my colleagues yesterday talked about the population modeling. So we are going to start thinking about how we build a population modeling. What are the components of population modeling and where those components are coming from. And if you want to practically experience creating those components, how would that be? So today's session is mostly about the covariate, the type of the population data set that we are using for our population modeling. Oh, it's off. Sorry. Awesome. So the component of our population modeling could be categorized in different parts. First, we talk about the type of the population data set that we are using as a reference or as a training data for our population modeling. And then we go to explore some of the settlement data set that are available at the global scale and are also freely accessible, which is quite important for many applications, including the building the population. And then we will also provide some examples about some of the covariate, common covariates that we are using in our population modeling. So when it comes to the population, our population modeling techniques, it doesn't basically just predict the population out of nowhere. So we need to have some kind of references. So yesterday we talked about the two different type of population model that we have in general. One is the top-down and the other one is the bottom-up. In top-down, often what we have aggregated population or projected population at some certain administrative boundaries. So when we use the population modeling techniques, we disaggregate those population totals into settled area. In our kind of uniform, like often product at WorldPop, we are producing 100 meter by 100 meter raster, which basically provides you an estimate of the population within that grid cell. For the bottom-up population, often we don't have a full coverage of the population. Sometimes you have done some sort of like survey, which have basically just focused on a small percentage of the population, or you have done other data collections throughout the country, which hasn't covered the entire country. So that type of data set provides you some basic information about that particular area that you have collected the data for, including number of household, like population characteristics, and maybe also going into detail about socioeconomic sometimes, and also about the type of the building. So when it comes to the building the bottom-up population, we are mostly dealing with this kind of small area. So a kind of ideal scenario for us to be able to use those kind of samples are something like this that presented in this slide. You have a kind of area which is fully enumerated. So let's say this particular area within this city has been selected for your survey. So an enumerator goes into that particular area and enumerate the entire area. And again, that area, you have a strict boundary for it. So then we will be able to basically always go back to look at that area and do some, run some kind of relationship between the population that we have within that particular area and other covariate that we are using for the population. So this is an ideal scenario for us for bottom-up population. We need to have that kind of small area representative across the country, and ideally have a geographic boundaries. Otherwise, if you have just only the GPS household location, it may not be possible to understand what is the geographic area that that particular data has been collected, whether X household has been included or not included. So we always prefer to have a strict boundaries for our sampling unit. So when it comes to the type of the data that we use for our bottom-up population modeling, we have different data set. The first one, we call it microcensus. So microcensus, it's also a type of like survey. Let's say you have, let's take an example like for Panama. In Panama, let's say they haven't conducted census, so we don't have a GPS household location across the country. And we would like to build up a bottom-up population modeling for Panama. Of course, ideal scenario would be you enumerate every single household across the country. However, this is quite costly. So what I can do, I will design my survey, which we always call it as a microcensus. So we will make some simulation, possibly stratification, to understand different population types across the country. could be geographic, could be climatic, any other characteristics or environmental factor that you can use it for your stratification. So once you have done that, then you will understand the landscape of these countries and also the population distribution. So what you can do, instead of, because you don't have budget to enumerate every single household, what you do, you will basically just collect, sample across the country, but must be representative. So let's say you collect around 500 for each of sampling unit. Then it will basically rely on the resource that you have, how many samples you would like to collect, and also the type of population, the country that you're predicting. Because if you're doing some simulation at the beginning, you will get an idea how many samples you can take that you can basically produce a reliable population, gridded population data. The second type of data set that we use, we have been working with multiple countries that they have done census. However, due to security challenges, they were not able to enumerate every single household. So the census data is kind of partial. So what we have done, we have used the areas that we are confident they are fully enumerated and use that as an input for our population modeling, bottom-up population modeling, and then predict for the areas that we don't have data. So my colleagues have already mentioned a couple of countries before, like we have done it in Burkina Faso, in Afghanistan, and a few other countries. So that is a second type of population data that we use for building our bottom-up population model. The third one is, you know that socioeconomic survey is a kind of routine survey in a lot of countries around the world. So every year, different institutions, they conduct socioeconomic surveys, health surveys. So within those surveys, they also target a small percentage of the population, which means only taking small samples across the country. So those type of surveys is also quite useful for building up our bottom-up population model. So these are the three general main kind of type of data that we have, we use for our bottom-up population modeling techniques. So a few examples. So here, if you look at this map, this is basically a type of the data that we have. So here is a microcensus. You can see the boundaries of all the sampling unit across the country. Outside the sampling unit, we don't have any information about the population. So what we have done, we simulated before and try to make sure that the data that we collect for this specific country are representative. So based on that, we basically randomly distribute our sampling unit, and you can see each of them, they have a boundary. So once you collect the data, you know that the enumerator has fully enumerated those microcensus for the entire country. Then once we have done that, we will use that as a training for our bottom-up population modeling and using covariate for predicting the population in the unsampled area. So we have different use cases that we have used this type of microcensus for collecting data. We have Nigeria, South Sudan, and Democratic Republic of Congo. That's where basically we designed the microcensus and collected data. Because in those countries, census has not been conducted for a long time. So we had to come up with the sampling unit across the country to be able to build up the robust population modeling techniques. So the second example, you have seen it also yesterday during the presentation, is the Burkina Faso, where we have partial census. So you can see that based on the map that we have the areas that the enumeration were not completed. So they were missing data. So what we did, we relied on the area that were fully enumerated and then used that in our bottom-up population modeling techniques to predict the population for the area that has high uncertainty or they haven't collected the GPS household location during the census. So we have like cases in Burkina Faso that we did the bottom-up population and also in Mali. So majority of the reasons, I think some of the countries in LACRO region, they have similar issues, could be due to security issue or what we have heard as well in Latin America, LACRO region is sometimes the accessibility is due to gated community that enumerators are not allowed. So, but in Africa, most of the time are due to security issues. So in one of our new project in Cameroon, we didn't have microcensus. We didn't have budget for conducting microcensus across the country. So we had to basically find alternative data set that could help us to build our bottom-up population. So in Cameroon, there has been quite few socioeconomic surveys. You can see in the slide, they have different type of surveys. So what we did, we basically used those data set that has been collected during the surveys to build our bottom-up population model and to predict the population in the areas that we don't have data. So we also have, not just for Cameroon, we have done it for other countries, example like in Papua New Guinea and also in Zambia. So that was just a brief introductions about the type of the population data set that we use for building up the population, bottom-up population model. So you can think about your country, like what kind of data set you have. If you want to build a bottom-up population in your country, then you need to think about this type of data set that we have mentioned. And if you have such data, then you can be confident that you can rely on them, and then you can build your bottom-up population model. Of course, there are uncertainties. It basically relies heavily on the quality of the data that has been collected first, and also how representative the data are across the country. Because if a particular population type were not surveyed, then the model output won't be that accurate. And also, if the survey are quite sparse, like they haven't covered the entire country, let's say quite representatively and geographically, then you may have high uncertainty in the areas that you don't have data for. Any question about the type of the data that we use for our bottom-up population modeling? Okay, so the second part, which is quite important, because when we predict the population, the first thing that it comes to our mind is where these people are. Because you may have the total population, you may have some kind of survey that has particular focus on small geographic unit across the country, but when it comes to the prediction, the first thing that you need to think about is, okay, where to predict the population? Where are the settlements? So within this kind of brief introduction, we will show you some of the example freely accessible settlement data set at the global scale, but some of them may not be available for certain location. But the good news is they are all like making an effort to produce more data sets that are freely accessible. So you can see some of them might be available for your country, some of them might not be. So as I've mentioned, so the concept of the settlement is a proxy for people, location with complete coverage of the study area. So of course, there has been a lot of kind of development over last decades around using high resolution satellite imagery, machine learning to extract the building footprints, building outline, building locations, and they have put all together to basically create the complete delineation of the settlement at different scale. So we have listed a couple of the data set that we think they are freely accessible for you, and we are going to provide like a brief kind of overview of each of the data set. Some of them, as I said, might be available in LACRO region, some of them may not be. So the type of the settlement that we are going to introduce are building footprints, build-up area, gridded building intensity, National Statistic Office building data set. So these are the type of like settlement that you probably hear more when it comes to the settlement. So the first one is building footprint. So this is a product that has been produced by Ecupia. And the source is Maxar and Ecupia building footprints that people are always referring to. So what they have done, they have used obviously high resolution satellite imagery across sub-Saharan Africa, I think for the entire Africa. And then what they've done, they have delineated every single building across Africa. So the shapefile for the building outline are not freely accessible, but at WorldPop, we have rasterized those polygons, and then they at 100 meter by 100 meter, and then we created some kind of statistical metrics like number of building area, and those raster data set are freely accessible. But unfortunately, it's only available for Africa. But this is something that, you know, maybe one day you will work somewhere and then someone asks you, I want to do X, you know, project in Africa, but I'm looking for the type of settlement, then you will be able to provide help and suggestion. The second settlement layer that is available is Google, which is also open. They have also used machine learning satellite imagery to extract the outline of the building. But unfortunately, the Google dataset at the moment does not cover the LACRO region. So it's not available. But you can see the tiles where the dataset is available, and you can freely download them. And of course, for each of the data set, we have given you a link. So whenever you have time, you can basically just go into the website and explore the data. So the other open source data set for settlement is Microsoft Building Footprint. It is available for Lacro region, but not for all the countries. You can see from the slide where the data is available. It's quite patchy across the region. But one of our colleagues, she has been working with Dane and uses the Microsoft built-in footprint. So far, she's happy with the data set for Colombia, but we don't know how it looks like and what is the accuracy for other places in the region where the data is available. The other very useful data set that is openly available at the global scale is the World Settlement Footprint. So this data set has been produced. It's a collaboration between the European Space Agency and German Aerospace Center and Google Earth Engine. And they are using also different like satellite imagery, I think, including Sentinel-2, Landsat. What they do, they predict the settle area using, again, machine learning. And the good news is this data set is available at the global scale. So they have different metrics as well, which is quite important for the population because some of those metrics are related to the population directly or indirectly. So we have like friction, total area, average height of the building, because some of the limitation that we had previously within our population modeling output, because we didn't have information about the building height, then we always underestimated the population in the kind of dense urban area or in places where we have high buildings. So within this data set, it will be quite useful for tackling those kind of challenges. The output resolution is 90 meter, and I think the current version is 2019. But we are hoping that those kind of organization, they will update the data and they will release it for the recent year as well. Another important data set that is available at the global scale as well is the built-up area from GHS, Global Human Settlement built-up surface. The important about this data set, it doesn't just give you the settlement, it gives you the type of the settlement as well, whether that is urban, semi-urban, or rural, which is also quite important for predicting the population because the density population distribution are quite varied across those type of like strata. So the raster data set you can download is available freely accessible at 100 meter by 100 meter. As I said, like we provided the link, you can always look at the data, download the data for your country and explore it. And you can basically judge which data set is good. There are specific output, maybe not at the global scale, but sometimes through our collaboration with our partners, we get access to specific data set for countries. Like in Papua New Guinea, so at that time, I think our colleagues were looking for some good settlement, and because of the tree cover and other challenges, they wanted to have a specific data set that could be basically accurate in the context of Papua New Guinea. So Planet was providing a settlement layer at 5 meter, which is quite high in terms of the resolution. And that was used in our population modeling output in Papua New Guinea that we did with the local stakeholders and UNFPA in Papua New Guinea. And of course, another important, freely accessible data set, not just for building footprints, for a lot of other data set, including roads, waterways, point locations, point of interest. Building outline is OpenStreetMap. So it has a lot of information that you can use it for different purposes. And of course, here the purpose is using the settlement layer for building the bottom-up population techniques. Another type of data set that we have is the data that has been collected through the National Statistic Office. So sometimes during, I mean, most of the recent census are quite modern. So they would like to basically, all of the countries are transforming from the traditional census to digital census, which means you have basically geolocated every single building or household across the country. So that kind of location of the building or household can be converted to create a settlement. So this type of data set also quite useful. Sometimes they are collected during the census cartography. So you can use it to create a settlement layer for your population modeling techniques. So throughout this kind of review of the data set that we have provided, so you will have the chance to go into those websites, download them, and throughout the practical session after this presentation, you will be able to basically open different data type in R, and of course, create a kind of interactive map, or let's say, use the base map, and then you can overlay the type of data set that you have, either with that comes from the sources that you are interested, that is available for your country. Then you can make a decision which data set is good for your country. So this is quite important for a lot of application, not just for building the population. You can use it for designing survey, for logistics, because it's quite hard to always just make a plan without knowing where the people are. So this type of like settlement, although they may not be very accurate, they may have missed some part of the settled area, but it will give you a high percentage of the coverage for the entire country that you're working, or for the specific location that you're working. So that was just an overview for the type of the settlement data set that are available, freely accessible at different kind of geographic location across the world. Any question? Who had the chance to explore the settlement data set before? Have you downloaded any of them? Had experience with any of them? Where did you use? For which country? Panama. What do you think? Is it good? For roads. Perfect. And Microsoft building in which country? Sorry, Colombia. And what do you think about it? Do you think it's good? Okay, perfect. Anyone else has experience? Please.
I have been using Google Earth Engine.
So
it's kind of hard.
Sorry.
I was saying that I was using, or I had been using Google Earth Engine for our work in smaller estimation in ECLAC.
Mhm.
And at first, you have, to get into the programming thing, but it's kind of, the effort is at first hard, but once you get into it, it's easy.
Yeah. Did you use any particular data set within Google Earth Engine?
Yes, we have been using 6 sets of covariates. It is pollution, night lights,
Mhm.
Urban cover fraction, crop cover fraction. There is an index of vegetation,
Mhm.
and some other that I can't recall right now.
Awesome.
Yeah.
Perfect. Anyone else has any experience with settlement or other covariate that they have used? Cool, no worries. Today is your day to experience the first kind of practical session on your covariate. So some of the example that we have used the settlement, of course, we use settlement almost for all of our population modeling because we need to know where the people are. And then we predict the population in those kind of settled area. So this is just an example in Burkina Faso. As I said, we had partial census. Census couldn't cover the entire country due to security challenges. Then we used the bottom-up population model and training data in the areas that they were confident that they were fully covered, and then predict the population for the areas that had security challenges. But of course, we use the settlement layer for this area. So in other cases, we are using like different kind of metrics from buildings. Could be area parameters, because what we have for the population, the type of the building, the shape of the building, the size of the building, building counts, and these kind of parameters are quite helpful for distributing the population, because we can use some kind of prior, let's say, classification to understand, to separate the type of the building that we have, and then use that as a kind of prior knowledge for assigning the population. So we are using like different parameters that are extracted from the building, because what we have from majority of those sources that they provide settlement, they have a polygon which basically delineate the building. So if you have a big building, then the polygon is big. Maybe the shape of the building, it changes the polygon. So those metrics can be calculated, and then each of them has a direct or indirect relationship with the population that we have. So sometimes we use those kind of information to be able to produce a more robust prediction. And of course, we have in other cases used the supervised or unsupervised classification algorithm to basically come up with some sort of like classes for the building that we have. You know that often when you apply classification algorithm, so the algorithm will look for the kind of the pattern that are common within certain location, and then it will basically create a cluster within that particular area. So based on the output, you will have different cluster, different properties, different characteristics. So which basically gives you the variations geographically across the area that you are planning to predict the population. And that kind of variation would be quite useful to derive a robust population prediction. So far, we have covered two parts of the component of our population modeling, bottom-up population techniques or component or input data set. So one of them was the type of the population or data set that we are using as a reference or a training data for our bottom-up population. And the second one was about the type of the settlement that we have and which data set is available and where can I find those settlement type. The final part that we have as a component of building the bottom-up population is other covariates that are quite useful for predicting the population, which are the like other covariates that are also extracted from sometimes, I mean, mostly from satellite imagery, but you can also extract other covariates from socioeconomic variable as well. So some of the common covariate that we are using in our population modeling techniques includes nighttime light, as one of our colleagues just mentioned. We have distance to hospital, distance to school, water bodies, vegetation cover. Like we have different indices that you can basically apply to your satellite imagery, like normalized different vegetation index or EVI, or even climatic variable. So you can basically extract those those covariate. Of course, the type of land use, land cover is also important for predicting the population. And obviously conflict data is also quite important because nowadays conflict is one of the driver for population movement, IDPs, and so on. So this is also like some of the covariate. I mean, you can basically sometimes for building a population, we can create 100 covariate. But at the end of the day, you run your population, you run your preparation for the building of the population. So first, you create your covariate, and then you will go for the covariate that you think are quite recent, are available, like accessible open source data. And also, it's very important that you check the resolution and also the spatial resolution, the temporal resolution, because these are quite important for creating accurate and reliable and recent covariate. So these are the kind of characteristics that you need to look for in the production of the covariate. So the first thing is whether this covariate is publicly accessible, because sometimes you may get a data set through a friend or a colleague or an institution, but you're working with an institution that they would like you to publish the output. So if the data that you're using is not publicly accessible, then by default, you can basically publish your data. Second, when it comes to the covariate, because we are talking about satellite imagery most of the time, so try to look for the type of the covariate that has high spatial resolution, because it's much more accurate. It gives you precise location of the area. And of course, the one that has like more temporal resolution as well. So if you are looking, for example, at the predictions of the population, like seasonality throughout the year, then that is also a very important variable that you need to consider in the production of your covariate. And of course, I mean, from the satellite imagery, you can extract like 100,000 of the covariate, but you need to also be careful what kind of covariate that you are extracting. So you need to think that the covariate, the type of covariate that you are extracting has some kind of direct or indirect relation to the to the population, or it has a significant impact on the population. So this is just a few examples. We will see some of them in the practical session, but this is just an example of the ACLED conflict data, which is also publicly available, and it gives you an idea where the conflict are going on. Then you can basically use that as a...
No worries.
So you can use that as a covariate, because nowadays a lot of UN agencies, National Statistic Office, they are struggling to basically get an idea about the distribution of the population, especially when conflict is basically come in, and a lot of people have just basically moved from one location to the others, and this type of data set, if they are recent, would be quite useful in your building the bottom-up population techniques for your country. So this was just a kind of brief introductions to the type of the input data set, the component for our bottom-up population technique. Do you have any question, concern? Something that wasn't clear before we move to the practical session? Awesome. So we are going to start the practical session for creating the covariate. But before that, yesterday there was some kind of confusion when it comes to the directory. So let's just use a kind of uniform directory altogether. Then every time you use that directory, and then you can basically access the data easily. So can I ask you to copy the folder that I have shared with you with the name Panama_workshop? Just copy that folder and paste it in on C drive, like directly on C drive. Yeah. So this is my C drive. When I open, this is my C drive. So just copy Panama_workshop. Then every time, if I call any data, I use this directory. So that's why we were talking about directory yesterday, directory. So some people have never basically used that in the programming. Why I have to use this link to connect to my data. So this is how basically it looks like. So if I click on my if I open my folder, it will give you a directory from C directly to my Panama workshop. So that would be my directory. So that's why you always need to have that kind of directory, correct directory to access your data. So please make sure you copy your Panama_workshop folder, not the zip one. You should have unzipped it already and then paste it just on the C drive directly. Anyone has an issue finding the folder? copying into C drive, because from today on, every day, we will use the same directory. So you always start with C drive, Panama_workshop, and then day 1, day 2, day 3, day 4. All good? Perfecto. So now, before starting the practical session, I want you to have a look at day 2. So what kind of folder we have, what kind of data set we have, because once you understand what kind of data we have in the folder, then when we go to the practical session, when I say we are calling this data set, then you will easily understand where this data came from. Okay, so let's go for day 2. So within day 2, we have 4 folders. The first one is data, output, script, slides. Obviously, you can access the slides from the folder that we have for slides. Any input data that we are using for this exercise will come from this folder, data. And we create another directory to save our output. So every time when you save the output, it will come to this output folder. And of course, you will see your script in the script folder. So let's look at the data that we have. We have already provided you with few covariate, which basically start from building count, which means we have a raster data set. Does anyone have an issue understanding the difference between raster and vector data?
I don't know what is that.
Raster data set, vector?
No idea.
No idea. Okay. So what would be the best way? Okay. Imagine you look at my face, okay? If you want to differentiate between vector and raster, okay? If you look at my skin, it's a kind of continuous kind of skin all over my face. But when you see my eyes, my nose, these are the kind of feature that we have. So it has a boundary, okay? So raster data set is always a continuous data, which basically depends on the resolution that you have. You always create something like a, a grid output. Like so you have value for each of the grid cell, like the skin that I have on my face. It's continuous for the entire geographic location that you have the data for. When it comes to the vector, vector is not a continuous, it's a discrete boundaries. So when it say I have a administrative boundaries for Panama, which means like you have a polygon or a line or a geographic location, a point location. So we have like 3 types: polygon, line, or just a point. So these are called vector. We often refer to the shapefile as well. For raster data set, it's always like like in most of the cases, you have a gridded like resolution. Of course, we have different type of raster as well, but most of the time we deal with this kind of data that we have, which is a continuous data set. And we have like different, of course, file type. We have TIFF, like a lot of other formats that are available for raster. But one of the mostly common used file type for raster is TIFF. But of course, you can use it. We can have like multiple format for raster dataset and also for the vector dataset. But importantly, what you need to know for the first start, how you differentiate between raster and vector is this kind of definition. So you either have polygon for vector dataset or line or a point location. Whereas for raster, it's continuous. You have a gridded either for the entire country or maybe, let's say, for the settlement layer, what we have, you only have the grid cell for the areas, let's say that there are people. So if you look at the entire country, obviously, they all match together. So you start from column 1 or column 0, row 0, and then you finish here. But in some data set, you don't show the areas that you don't have value. You possibly just call them an NA or other values. So you can see you have a raster for the entire country, but the gridded output that you see is only available for specific location because you only have a value for that specific location. However, the raster data set, the extent is like that always. So start from here until here. Any other? Do you understand? Does anyone has any issue with differentiating between raster and vector? Okay, so there is another important element about data, especially for us. We are talking about the geographic location. So we have two different terms as well. You need to be very careful. First of all, when it comes to plotting the data, you always hear about the geographic coordinate system or projected coordinate system. And you open your R, you're quite excited to run a specific syntax with your data, and then suddenly you get an error because you're using two data sets that may have different spatial projection or coordinate system. So you need to be very careful if you are using multiple data sets and you want to do something with all of them together. They have to be in the same projection or geographic coordinate system. And when it comes to the raster, the other important thing that you have to always remember, they have to have the same extent. So if you have two raster, for Panama, same country, they are both rasters, but the extent, the number of row and column for raster 1 is different to the raster 2, then you can't basically work on both raster together. So if you are trying to run something for applying something for both of them together, it doesn't work because they have different spatial extent. So you straight away get an error because the number of row, this is your number of row, number of column are not matching. So you have to be very careful always, because you are going to learn about R and you are going to work on geographic data. So two things are very important: geographic coordinated system or projected coordinated system. They have to be in the same projection or geographic coordinate system. And they have, when it comes to the raster, they have to be, the size of the raster has to be the same in terms of number of row and column. Otherwise, you can't operate those data together. You can open them separately, you can show them, you can plot them separately, but when it comes to this, like stacking together, applying cropping, masking, other kind of operation, it doesn't work. So the other important, because this kind of like this kind of component is very important when it comes to the dealing with the raster and vector data set. So that's why I'm trying to tell you before we go into the practical session, because every time you will face this. We have two other kind of, for those who are familiar with the GIS or R, we have two other terms that we always use, is geographic coordinate system and projected coordinate system. So when you open a vector data set or a raster data set, if that raster or vector data set is in geographic coordinated system, it will give you everything in degree or decimal degree, which is not a usual unit for area or for distance. If you want to calculate something in meter, kilometer, or some of the usual unit that we are familiar with, then you have to convert it to the projected coordinate system. So geographic coordinate system, projected coordinate system. Geographic coordinated system works on allocating geographic area on the Earth's surface as a coordinate. So it's not flat. So we have like this kind of round of Earth. So that's why it's always in degree. Whereas for the projected coordinate system, it assumes that we are calculating everything on the flat area. So that's why you can easily measure in meter, kilometer. So it's very important that you understand those differences. Once you get it, and that's it. I mean, you will be easily working with different data and different projection. And there is always an easy way in GIS software are to convert one data set to the others. Anyone has any question? Anything that you don't understand, you want me to repeat? Okay. Okay, so let's go to the practical session. So this is the data that I said. So we look at this, the type of the data that we have. Those that looks like in a kind of object or a photo kind of shape, these are raster data set. And it doesn't show the extent, but they are all ended with .tif, which is a file format for the raster data set. We have one data set, which is called microcensus. And you can see that is how S3 system works, GIS, ArcGIS. They always save the vector data set in multiple data type to basically store all the geographic coordinate system and so on. So so if I want to basically share my S3 shapefile, I have to share all of them together. If you miss one of them, it doesn't work. But in most of the GIS software, if you open the data set correctly, it will always show you just only the one that ends with SH P, which is the shapefile. So we have a couple of raster data set, and we have one shapefile. So the raster data set, we have building count, building maximum distance, distance to ACLED, which is the conflict data, GHSL built up, which is one of the settlement layer, grid ID, and we have microsensor shapefile, and we have nighttime light. So these are the type of data set that we recall in our practical session. So when I say in the art session, when I say I want to open building count, basically I need to make sure that my directory comes to this folder, and I have put this name in my script, and then it will basically call this data. Okay, so let's go to the script and open it, and then start the practical session step by step. Okay. Is there any question? Because I was told that this is a coffee break. Then we can. Any question before we go to the coffee break? Do you think that they are ready? Oh, okay. Please. Sorry, 1 second.
El archivo que tiene el día 2, que tiene el iconito rojo, ¿esta es una aplicación o microcensus? Con el iconito rojo ese, no veo desde acá bien. Ese, ¿no? Aquí está.
So we have like different data type here. The one
Yes.
with the red icon are the raster data set. So this one, building count, building max,
Sí,
distance,
entiendo todo eso, menos este.
GHSL,
Sí, sí, sí.
grid underscore ID, nighttime light, they are all raster data set.
Estos son parte del mismo.
And the format is TIFF. So if you look at the folder, and then maybe show the type of the data, then it will show you the end, which is .tif.
A algunos les va a aparecer, como le apareció allá, uno de estos archivos le salió a ella como con un icono para Visual Basic. De pronto a algunos les salió. Lo que pasa es que el archivo de shapefile, los shapefiles tienen, como dijo Sachil, como una tabla Excel o un archivo de base de datos que algunas veces la extensión es DBF y lo lee con el programa, o sea, lo muestra con el programa que tú ya tienes instalado. Pero siempre el archivo, un shapefile, siempre va a tener adjunto estos, siempre 1, 2, 3, 4 y 5 archivos, siempre son los básicos. Y siempre tienen que ir juntos, como dijo Sacho. Pero cuando ustedes lo van a ver en el QGIS, en el programa para analizar los datos espaciales, solamente les va a aparecer pero siempre tienen que ir esos 5 juntos. ¿Ok?
If you change the view and then you go to details, you can see another column, which basically tells you the format of your data. So the first one is TIFF, 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 and then so on. Any other question? have a good coffee break. How long do we have for the coffee?
¿Cuántos minutos?
I think it's 15 minutes.
20 minutos.
Yeah, I think because they need some time to download the packages, so 15 minutes would be, yeah, please. 15 minutes, please. So we will be back in 15 minutes if you don't mind.
Then you can see people.
Welcome back, everyone. Hope you had a good break, nice coffee. So time to explore some practical sessions on hands-on training on how we basically extract variables, how to deal with different data type, vector, raster, using our script. So it's quite exciting for those that you have not used R before. This is something that you look at it, you produce the output and say, wow, I can open raster dataset now. I know how to open shapefile. And I know how to do a few kind of tricks around, different type of the data that we have. So, and then we are going step by step to get it harder and harder. And hope that kind of excitement will go up again as well. So within the the folder that we have, we shared with you, Panama_workshop. We have day 2. Then when you open day 2, we have a folder specified for script. So please open script folder. Sorry. And then we have 2 R script. One of them is covariate extraction. The other one is regression model. We are not yet at regression model. We need to basically warm up first. So we are going first to the covariate extraction. So let's double click on covariate extraction. So if you have RStudio, R, you have already downloaded, and I'm hoping that everyone has it in your computer. If not, you can basically open the R script, but I'm assuming you all have it. Then we will have this beautiful interface. But some of you have a different appearance for your R. This is my preferable choice. If you want to change it to this interface, I will show you how to do it. The only thing that I like it, it will give me always this nice color. So I know what am I doing. So before going through the practical session, I will give you the options to choose the one that you like or this appearance that I have. So you go to Tools, okay? From the main menu of your RStudio, go to Tools, the final option, which is called Global Options. Click on that, and then a new dialog will open. And then we have one option here, which is called Appearance. That's where you can basically change the interface of your R. So if you click on Appearance, you see mine, I am using Cobalt. So it will give you this kind of nice interface. And it's much more exciting to work with. because I like colors. But if you don't, you can just stick with the plain one that we have. So once you choose the cobalt, and then you just say okay, and then it will change your interface to this option. Are we all good? Perfecto. So now, by default, we have some library that we need to install. I know some of you have already installed them. If not, we are going through one by one because you need those libraries to be able to run the script. Otherwise, you get an error or a suggestion. So one small recommendation for you all, from now on, you are a R user. It's very important every time when you run a line in R, you need to be very careful what you get as a result. Look at for the script when it runs, what kind of information will gives you. Because sometimes the challenge, the issue that you face can be solved from the information here. So a good programmer, what a good programmer does, it always look for the kind of information that you get from here, and then copy, if you don't understand, copy, browser, search for it. You get a solution, 100%. And sometimes you probably just run something and then you get an error and you say, what should I do? I mean, it doesn't work. But you can see here, it will give you a solution. This script that you're running needs to install X package. So simply install that package and then go. Or sometimes even it asks you, this type of package that you are working or a line, it needs this specific package. Do you want me to install it? Yes or no? You can just say here, yes, I want, please. I mean, don't add yes, please, okay? Just yes, and then it works. So always look very carefully on this site, okay? If you get an error, you don't know how to solve it, just copy it, paste it in browser, and then you get a solution. Someone has done it before. So that's for sure. So by default, some of those lines are not active, so you can't run. If you put hash in front of any line in programming language, it will make that line inactive, so you can't basically run it. But if you want to activate it, you just remove the hash, okay? So let's just try. I don't know how many of you have already installed those packages, but okay, one important information also is very, very important. You don't have to always install packages every time when you open R. Let's say one package that we are using is Terra. Okay, you install it to your computer. You don't need to install it every time when you open. But what you need to always call it at the very beginning. You need to use this line, library, to make it active. And then that package is ready to use. But you don't need to install it again. It may ask you for update at some point. That's fine. But once you install it, that's it. You have it forever. But what you need to call the library at the very beginning. So if you have installed those packages that are in blue, if you just call them, if they have been already installed, they become active. If they are not installed, it says there is no such a package in my in your computer. So you have to go and install it. So let's just go line by line. So for me, I have installed all of them. So if I click run one by one, you can see it doesn't give me any error. It will make every single library active and they are ready to use. Okay, so for me, everything works fine. How many of you has got error? Okay, one. Okay, so what you do, so we go to one step before. We go one step before, and then you basically remove the hashtag, and then you will see install package Terra will become an active. So it's ready to run. So if I just remove, you see, my install package Terra has become active. So you can basically just click run for this particular package, and then it will install it. Okay? And then you do the same for the second, third, fourth, until the end. Once you have done it, then you have to rerun the library again. Is that clear? How we, anyone? Okay, so I will repeat it again. Okay. What I do, I am just removing the hashtag, okay, for all of them. Yeah. So, sorry. I yes. I'll repeat it. Don't worry. So when you have hashtag in front of your your line, it will become just a text. So you can't basically run that line in your R. So if you want to basically describe something in your R script, then you need to basically start by hashtag and then explain what this code means. And of course, there are different ways of making it fancier, but the simplest way is you start with hashtag if you just want to have a text. But if you put a hashtag in front of a syntax or a script, a line in your script, that line cannot be run. So if you want to run it, you have to remove or delete the hashtag. So at the beginning, we had hashtag in front of each of them. Even if you come here, run, it doesn't work because it has hashtag. But now we removed all of them. So now you can go one by one. But when you run a package, please wait until the sign tells you, it has been installed. If you have a kind of red symbol here, say that means that's still running. So once that one finish, and then go to the second and third and fourth until the end. Yeah, just wait for it until the red kind of sign disappear, and then you can go for the next one. Okay, good, perfect. Yeah, good. Yeah, good. All good. All good? No? What's the problem?
Blocked by my situation.
Oh. Okay, okay. All good?
Yeah, could you explain me briefly what this package made?
It will be hard because it has a lot of information for each library.
Yeah.
But when you have time, what you can do, you can just copy and then paste it in browser, and then it gives you all the information because each package it has a lot of functionalities.
Yeah.
Yeah. So we can't basically go through each of them, what each package does, because it takes days to explain. But but what you can do, you can just copy, and then when you have time, copy and then paste it in the browser, and then it will tell you what the package is about, what are the functionalities, and how you make the argument and everything. Yeah, no worries. Yeah, thanks. Anyone has any issue? So once you have installed all the packages, please go to the following step, which is just running library for each of the package. Then if you don't run into any error, it means that your packages are fine. They have all been installed.
I have tried the SMP map package yesterday and the raster too, and I'm having a problem. I just could install a new flag.
Let's forget about this one.
Okay.
Let's go for the next, for the second, day 2.
Okay.
Yeah. We're just about to start. And we told them that we have changed the directory. So if you want to basically follow the same instruction, you can copy your Panama_ workshop into C directly.
Okay.
And you always have, C Panama_ workshop day 1, day 2, day 3, like this.
Okay.
But yeah.
And then it's covariate.
Yes.
Covariate extraction nature.
Yeah. So let's run the library, see if you have them.
No.
Okay. So let's just start from the very beginning.
Okay.
Yeah. So yeah. Then run. Oh, the other one. Sorry. Yeah. Okay. No worries. Once you finish, and then you check if they are all good. And if you want to change this to the same, do you want to use the same? Because it's much easier. Okay. Appearance, because I always like color like that. But if you want to skip, okay. Sure, no worries. Are we all good? Anyone need any help? Can you please raise your hand if you haven't managed to install it yet? You're still waiting. Can you please raise your hand if you haven't managed to install the package yet? You're still waiting. So we are good to go? Okay, I don't see any hands, which means we can go to the next step. Yeah. I wanted to show them like what are the mistakes and then. So before we started the session, I explained from now on, if you have copied the Panama _ workshop directly saved on C drive, sorry, then you will have this directory, C/Panama _ workshop. Then we have to use that as a kind of directory, always starting from there. Okay, the script that we haven't set that directory. So we need to make sure that is identical to our directory. If you add 1/ or miss 1/, then it always gives you an error. Or if there is a spelling error, or if there is something missing, then it tells you there is something wrong. So let's make sure we set our directory as it is. So currently we have the drive. We have the drive path, which is C/Panama, and there is a space and workshop, which is not correct. What we can do, you can add _ and also make the W capital. So if you have copied your Panama _ workshop on C drive, this directory will work for everyone. But if you have saved your folder somewhere else, then you need to make your directory. I don't know exactly where have you saved it. So unless I come and look at your computer. But if you have saved it on C drive, we can start always by that. So we have also added 1/ at the end because we are trying to basically tell the directory that we have other folder after when we go inside to the Panama workshop, which is day 1, day 2, day 3, day 4. So that's why we have a slash at the end. So, so now, if you run that line, the R will set your directory for C drive and your Panama workshop folder. Okay? So just click that line, run that line, sorry. If you have done something wrong, then it doesn't give you the output like drive path and then C Panama workshop and then so on. So if you have done a spelling error or the slash is missing or something, then you get an error. Otherwise, the output should be identical as mine. Okay. Anyone has any issue? All good? Excellent. So when we become a programmer, you advance your skill, you need to make variables. Okay? So you're not basically every time you want to set your directory for X and Y and Z and so on. So what you can do, you can make a variable. You say, okay, every time when I call this name, which means my input data. When I always call this variable, that will be my output folder. So that's what we are doing in the next step. So what we have 2 lines, okay? My input path will be always for you to be able to understand what the directory means. So it says input path. So that is the name, the variable that we have for my input folder, okay? Whenever I call this variable means my input data. So paste means the directory that I have pasted here, okay? So it will basically paste this little directory that I have at the very beginning for the main folder, and then it will add the rest of the directory, which is, we have already added 1 slash at the end of Panama workshop, and then it will add day 2 and then data. So it will be C Panama workshop slash day 2 data slash. So that will be a directory for my input data. Is that clear? I don't know.
There is so the like in tools or something global. In the Google. Something in global is it?
What is the question? Sorry.
No, they wanted to make it bigger because they can't read what you.
Okay, now it's better? Okay.
Yes.
Okay. Okay, sorry about that. So you can see our main drive path is C Panama workshop slash. Don't forget that slash. If you forget that slash, you need to add it here. Otherwise, it doesn't understand. Okay? From one folder to other, you need to have a slash between. So now, if you click on the second line, it will create a directory for your input data. And then if you run the second line, it will create a directory for the output folder. So everything that you are producing, you can save it in that folder. So let's just run one by one. Input path, run. Output path, run. So now I have set my main directory and I have two other variable, two other directory, which I have the name for. Data, my input data, and I have a folder for saving my output data. Okay, does that make sense? Do you understand now why we are doing all those slash like directory things together? Okay, good. So now you remember I have shown you day 2 data folder. Okay, we have some data there. So how am I going to call that specific data? The first data that I am working with is my shapefile, which is called microsensors. Yeah, so in R, because when it comes to the type of the formatting of your file, whether it's raster or shapefile or other format, you need to basically understand that you need to use different functions to be able to open each file type. So it's not just, you just write and say, I need my shapefile / and then open it. No, each of them has a functionality. As I said, you're not supposed to learn everything today or this week, but you will be introduced to the functionality. Then you will basically use it again and again, and then you remember. Because I know there are a lot of things that we're introducing. It's not possible to memorize everything. So now, first data set is the shapefile. I want to open it. The way that you can open a shapefile is reading it using a line like that, which basically designed to read vector dataset in R. The function is stread. And of course, what it does, it pastes the directory for the data. So what is the name of directory for the data is input path. So input path from the above, it will basically just give all the directory together, C, and then Panama Workshop, and then day 2, and then data, and then you call the type of the data that you want. So that's how basically paste and then the variable of input path work. So let's run this line. So now we will have the opportunity to look at the information for that specific data that we would like to read. So R gives you some summary, which is the data that you are opening is S3 shapefile. The name, it gives you the name. It gives you the directory. So you see, Panama Workshop day 2 data, and then the name of the data. So we started from the input path. So that's the directory. And then it's a S3 shapefile. And of course, it gives you, we said we have 3 different type of vector data set. So this one is polygon. So it gives so the coordinate system that we have is WGS84. So I have given you a brief descriptions for the type of general kind of geographic coordinate system and projected coordinate system. Each of them has different type of like projection and coordinate system. So you need to basically also look which projection or coordinate system is good for your country. Like for example, for projection, they have created a kind of longitude, latitude line. So they have divided the entire country to kind of tiles. So that says this is, for example, projected WGS 1984 31N or 32S. So based on the geographic location of your country, then you look at that map, global map, and then you'll be able to pick up which projection is correct for your country. So here is just a global coordinate system, which is WGS 1984. So that is just a summary of the descriptions of the data that you have. So now we are going to the next step, and I want to look at the variable in the shapefile. So if I run names pop shapefile, so it will give you a summary of what is the component of the shapefile that we have. Okay, so we have a column with the zone, EAID, one column, and we have one column for the pop and then geometry. Geometry is always a kind of default that you get an information when you read a specific shapefile. So now I have the shapefile, okay? This is very important because all of you are working in different institutions, and part of your job is you create data and you want to present it for the people. But you want to present it in a way that people love your presentation, understand. So this package, one of the packages that we have installed, is super helpful. So what it does, I have a shapefile, okay? I want to see my shapefile, but I want to also see a base map behind my shapefile, which basically gives me where am I or what type of base map I am using, because we have various type of base map. We have high resolution satellite imagery, you have OpenStreetMap, you have terrain, you have slope, like different kind of base map. So based on your interest, what is the interest, why you want to present this, the base map, then you can change it to that particular base map. For today's presentation, we are overlaying our shapefile on OpenStreetMap. So the function, the package that we have installed, which is called tmap, which will give us that kind of opportunity. So for presenting the output, visualizing, so this is the syntax that you can use it. So if you just run, and then the following section as well, what it says I want to present my shapefile, and you can also call for the specific column within your shapefile and also the base map that you have, that you want to present your data with. So if I just maximize this, so you can see this is the shapefile that I have. So what did I arranged? I presented my shapefile, and within the shapefile, I have a column which represent the population. Okay, so I have just given a graduate scheme for the color, which is by default. You can also change that, but we don't want to make it complicated for you. But for now, we present the shapefile, and then you can identify which column or which variable you want to present within your shapefile, and also which base map. So shapefile, and then I have the column for the population, which I have specified, and I have the base map as well. Then you will be able to see your shapefile or raster or any other data set that you have. Of course, you may have asked how this works, how this package does that. It's all about the programming techniques. They have API access to different servers. It will basically does all the things behind for you, how to access the base map and how to bring it to your R and stuff like that. This is something not many of us know how it works, but it's quite important that you know how the technique works, not just all the kind of operation behind, because it gets quite complicated sometimes. So now, if you have a shapefile or a raster, and then someone tells you, can you please show me how this data looks like, and also present it on OpenStreetMap or other base map, how to do that, then you have a way of doing it. Very simple. If you want to change it to different base map, then you can basically search for tmap, your package, and then it gives you all the information, how to call if you want to change the base map from OpenStreetMap to high resolution satellite imagery, or SLOP, or digital terrain model, things like that. So we have different base map. But as long as you know the principle, the context, then it will be quite easy to change it. Anyone has any question? Anything that's not clear? Okay. So let's go to the next step. So there is a so you will hear this word, this terminology a lot, because sometimes if you are dealing with a lot of covariate, people say, stack them together. So for those that are not familiar with this terminology, so let's say I have a couple of raster for the same location. One represents the slope. One represents the distance to road. One represents distance to school, okay? So if I want to stack them, because I want to run something through the whole raster dataset together. So what does stack mean? First of all, you need to make sure, as I said, you will hear this a lot. You need to make sure they are all in the same geographic coordinate system or projected coordinate system. Okay? First thing. If not, it doesn't work, because we are trying to operate few data set together. Second, are they all in the same spatial extent? Yes. Then it works. No, you have to basically do some kind of clipping or masking to be able to put them in the same spatial extent. Then once you have, you're sure that all your data set are within the same projection or coordinate system, and then they are in the same spatial extent, then what does stack mean? it means I will have different layers, like all together. The first one, second one, third one, fourth one. So if I click on one pixel, if I have a good software that can basically read stack, it will show me a value for each of the pixel from those data set. So first one, second one, it depends on the value that you have. So it will be stacked, like first raster data set, then second, and then third, fourth, until the end. So that is a stack of covariate or a stack of raster data set. It's only used for raster data set. Okay, so when you hear stack your data set or raster, so that is the concept of stack. Okay, so now we are going to extract continuous raster. But before that, we will need to basically import all those data sets and to be able to open them. Because the thing that we did with the shapefile, we need to use some specific functions to be able to open shapefile. It's the same for raster. But once you learn for both of them, it's exactly the same, unless if you are changing your package. Because calling a raster and vector data set could be different if you are using different packages. So just make a note of that. Okay. So now I want to basically list all of my raster data set that I have in my data folder. So this is my day 2 data. I have quite few raster data set. I want them to be listed all together. So this is the function raster underscore list. So list file, this is the functions that you can use for listing your data. And of course, you need to use your directory, which we have already set for the data folder. And then what kind of pattern, because you may have 100 raster data set in your folder. They might be in different formats. Some of them in TIFF, some of them in other format. So you can also specify what is the pattern, what is the extent, what is the format. So if I say .tif, it only lists the data set with that particular extension. Okay, because this is very important. Once your programming skill advance, then you basically just bring data from one folder to the other folder, this type of data, this. So this is the way that you basically separate different formats. So if I run this, then it has to basically list all my file, all my raster data set that has the extension of .tif. And then what I would like to do, because my colleague basically added quite few covariate in this folder, so he wanted to exclude 2 of them. So we don't want to basically have all of them in the stack because some of them are not relevant. Some of them are not covariate, let's say. So the second line would be basically just dedicated to exclude 2 of the raster data set. So if you click, so those 2 raster that we want to exclude is grid ID. If you look at the folder, we have grid ID and we have building count. So we want to exclude them. So if you run this line, and then it will basically exclude those two particular raster data set. So now, first, I listed my raster. Second, I excluded 2. So now I would like to see what has left in my list. So you can just click raster list, because raster list is the name of the variable that we have created. So if I click raster list, you can see the rest of the raster data set that we have been listed. Does that make sense? Any question? Okay, cool. So now, as I said, we want to stack the data. So the functions what is? I don't think this is stack. This is just calling the raster. Count raster. Okay, yeah, okay, perfect, yeah. So functions for stacking the. Okay, so as I said, for the shapefile, we had a function to read shapefile. Here, for this particular package, you need to always remember that you use RAST, which is the function for calling the raster data set. And then that's how you basically structure your line if you want to create a stack of raster data set. So what it does, it says, so this is the name that you're creating for this variable. It says, bring me all the raster that we have in that particular directory, and then stack them. Okay, so let's just run. So now we have basically stacked all of them together. So if you want to plot, see what the data looks like, then you go for the next line. Plot is always a function that you can basically use it for visualizing your data. Then you can see the 4 data set that we have been presented on our screen. So you can see one of them is the building maximum distance, GHSL, nighttime light, and distance to the ACLED, which is the covariate for conflict. Please. Sure. No worries. Absolutely. Sorry, let me just give you mic. Yeah.
So your map is from OpenStreetMap, and it has, you are putting a variable on the top of it. So the first question is OpenStreetMap always having like the geographic coordinates? So you need to have the variable geographic coordinates to match it. So how can I see what's the identification variable in OpenStreetMap so I can link them? The second question.
Sorry, one by one. Okay. So one of your colleagues asked, if I understood correctly, it's about the projection, the coordinate system, because we have plotted one of our shapefile on the base map. Whether it's important that your shapefile has the same projection as your OpenStreetMap, No. The same?
ID variable to link the two. So
No,
how
no.
can I know that the base map, like if I have the same coordinates that they correspond with my data in my shapefile?
Yeah, exactly. I mean, often, if I am not mistaken, the base map for the OpenStreetMap, it's in geographic coordinate system WGS 1984. So you can double check, but I think that is the coordinate system that they have. So if your data in whatever projection or coordinate system is, you can always overlay. But sometimes if the projection or the coordinate system is completely different, then it doesn't work together. But some of the projection coordinate system are very close to each other. So it doesn't really have a problem. But some of them are quite far away. The projection, the methodology is completely different. So when you add your data, you see like your shapefile is here, your base map is here. But WGS is something that is very common and people just using it for visualization, but it's not projected. If you want to calculate measurement like distance in meter, kilometer, then WGS coordinate system doesn't help you. Okay. So yeah, even if they are not in the same projection, you still be able to present, but it may be kind of a bit lagged together sometime.
Okay, so it's double GS. So I need to see if it doesn't matter if they are not exactly the same, but they need to be similar. Yeah, somewhat.
Exactly.
Okay. And then the other question, so you have the TIF images, right? The polygons. And then you have this variable. So what you're calling raster is the polygons.
No,
or are the variables?
Yeah. So we have in the folder, we have two different file types. One is raster, and if you look at it, we have the extension of TIFF for it. Yeah. And we have the shapefile. So each of them has their own way to be open in R. So it has like specific function. So we have used one function to open the shapefile, and then RAST for opening the raster dataset, for calling. Otherwise, it doesn't work. Yes, yes. So the first thing that you do in R is, okay, you set your directory, and then you have that data in your folder, okay? So each data set has their own way to be called prior to visualization, okay? So if you want to, let's say, multiply your raster data set together, if you want to multiply your raster to 100, before even doing that, you need to make sure that you have a correct way to call that specific file type. So the correct way for shapefile, we had it in the script. st_read, and that's how you basically read the shapefile. When it comes to the raster, then you need to always add RAST. So that's how you basically call it. So once you call your raster like in this way, then the R understand that you're calling a raster. And then it's up to you what you want to do later on. You want to present it in tmap, you want to multiply it, you want to do a stack, things like that. But first, you need to call it correctly.
For the raster. Hello.
Could a raster have more than one layer or just one layer?
So that's what we call it stack. Or sometimes in some of the raster output, they would basically just compile like several layers. Like if you look at the NASA website, and then you look for, I don't know, temperature, okay? So for saving the space, what they do, because it's a temporal resolution, sometimes you have data for every day or every hour. So what they do, they basically have different layer, they stack them together. So that's how we call stack, like one layer, second, third, fourth, and then each of them represents something. Like one could be temperature for 500 meter, one could be representing the quality of the data, and so on. So that is one way. The second way, where you have more than one layer, is when you have several covariate, like what we did today, and we want to just stack them together. So in that case, you will have multiple raster layer in one file, in one TIFF, for example.
Sorry, so what you call covariate are pieces of polygons? Because it's
So
not variable.
we, at the very beginning, we talked about the difference between raster and vector. So I explained to your colleague, if you look at, let's say, a face, the skin is a kind of continuous variable. So that's called raster, because you have a continuous variable. It could be like a grid or a point layer or something. It's a continuously for whole my face. But when it comes to my eyes, I have a feature. So I have a boundaries. When it comes to the eyebrow, I have a line. So that's a kind of major difference between raster and vector dataset. So raster is a continuous variable. You save it as a kind of raster format type, and it's continuous. And most of the time is in a form of like grid. It has a spatial resolution or maybe point as well. But when it comes to the vector, we have three types. They are not continuous, they are discrete. We either have polygon or line or just a point location, like point layer, polygon layer, or line layer. So when it comes to the raster, let's say we have two type of like, in terms of the visualization, okay? Don't mix that in terms of the visualization. So often or always, the raster data set that you have, it always starts from here, row number 1 or row number 0, column number 0, and it finishes here. So the whole data set, the spatial extent that you have is a grid. Okay? And that basically gives you the spatial extent. That's why we say it has to be the same when you are working with two raster. But for saving space, sometimes what we do, we basically call the areas that we don't have value as an NA, or we don't store any value. So what we have, let's say if you have a country and you have a raster data set which represent the settlement, then you have only the pixel with the values. Like I have one here, maybe something like that. It's not really raster exactly. Apologies for my bad drawing, but yeah, something like that. So, sorry. Yeah, so it doesn't have to be, it's already in this format, okay? But it doesn't really show you the areas, the value for the areas that there is no value. So that basically saves some space, but still the spatial extent, it basically starts like that. Number of row and column. Any other question? Okay, no worries. Any other question? Does anyone has any concern, question? Please. Mm-hmm. Yeah. Can you repeat your question, please?
Yeah,
Just for them to understand as well.
well,
Thank you.
It's about the size of the pixels. For example, you are stocking like 3 or 4 layers. On one of the layers, the pixel is like 5 meter by 5 meter space of the earth. And the other one is like 50 meters by 50 meters.
Mhm.
Does the program
Yeah.
use some special techniques to solve that?
So, well, first of all, when it comes to the different layers, if you want to work with all of them together, they have to be in the same spatial resolution. Because once you compare 5 meter spatial resolution for slope in Panama to rainfall data with 5 kilometer, by default, you understand that the 5 meter has many row and columns, whereas the 5 kilometer could be just, I don't know, 100 or 1,000, something like that, which means like these two are not compatible together to work together. Like if I want to stack them or if I want to run any analysis for both of them together, you can plot separately. Okay, so when it comes to the storing, so always in raster data set, so you either have a grid or you can also have a point for raster. So it's also the same. So based on your geographic coordinate system that you have and the satellite imagery data set that you have here, for example, you have a row satellite imagery. Okay, so within that row satellite imagery, you have information about almost everything. Okay, so there are specific, for example, index that you can apply, and that index has been developed, let's say, to extract vegetation. Like, for example, normalized different vegetation index, which is NDVI. So what the index does, it uses a formula, and basically it will only give you a value from 0 to 1. 0 means no vegetation. 1 means high and healthy vegetation. So when you basically extract that information, because it's already geo-referenced, and then based on your resolution, it calculates that value for each of the pixel that you have. So that's how you basically get those information. If you are using, for example, distance to road, you don't have raster at the beginning, but you have the road, and then you have functions in R or in GIS software. You basically create a raster using some methodology to calculate the distance. So the output of that functions or tool will be a raster. So for each grid, we'll give you a value and say, this is the distance here. Next grid is this, like this and this. It's a continuous variable. So the value within that grid represent the entire grid. Does that make sense? Yeah. Any other question? Okay.
Hello. Okay. I just wanted to say that once you upload a sorry. switch. Una vez que ustedes suben cualquier rasta a R y R lo lee, ustedes pueden poner un command que se llama str, str y el nombre del raster, y les muestra la estructura del raster y les identifica qué tipo de rasta es, qué resolución tiene, qué proyección tiene, qué tipo, qué tamaño de la grilla tiene, y así también les ayuda un poco como a identificar qué tipo de archivo es y cómo es la estructura del archivo. Así lo pueden cuando estén analizando los datos y para pueden visualizar qué tipo de datos de archivo están trabajando. Okay. That's all I want.
So is there any question before we move to next line in our script? All good? Happy? Or it getting more complicated, or things still good? Yeah, it's not very complicated. Yeah, so we are just warming up. Cool. So now we are going to the next step where, as I said, so if I have a raster data set with a specific coordinate system, and I have a shapefile, if I want to apply some zonal statistics. Zonal statistics is another terminology that you hear a lot. So I have a polygon here, geographically located on this particular location, and I want to calculate values from another data set. So I have a polygon. Like, for example, often, I mean, you can do it for raster as well, like raster to raster, but I have a zone. Let's say I have a polygon, or I have a big pixel raster data set here. You often hear zonal stat or a statistic summary based on zone. So what you do, let's say I have a raster here. So what the zonal stat does, it basically plot this polygon on this raster, because they have to be in the same coordinate system or projection, and then obviously for the same location. And then what it does, it calculates the statistical summary, like, do you want sum? Do you want mean? Do you want standard deviation? So it will basically calculate everything based on this geographic area for that particular polygon. If you have multiple polygon together, like, and then it will calculate for each zone. So that's why it's called zonal statistics. So you can use shapefile and raster dataset as a base. So you have slope, you have distance, you have population, any continuous data set in your raster, and you want to summarize it in your administrative boundaries. So that's a zonal stat. Sometimes you want a zonal stat not using the vector data set, polygon. I want to just use another raster data set as a zone. So it does the same. Okay, so now what we are trying to do, we have a shapefile, which is called microcensus, and we have a couple of covariates for the same location. I just want to do some kind of statistical summary for each of the polygon. Does that make sense? Perfect. Okay, so first of all, my colleague realized that the shapefile is not in the same projection of the raster. So you're lucky, you have already a line in your script that you can convert one data set to another projection or coordinate system. So the line for that in R is number 65. So I would like to convert the coordinate system of my shapefile to the raster data set. And I'm sure you already know, we don't want to convert the raster data set because there are quite few. Of course, you can do the same, like you can convert all of them if you think the shapefile has the right coordinate system. But if you want to be more kind of, if you want to do something quickly and you have like 10 raster in one coordinate system and one raster in another, easiest it will be like just convert one to the rest of the data set. But as I said, it depends which one is correct. So you have to always rely on that. So running this line will basically convert the coordinate system of your shapefile to the coordinate system that we have for the raster dataset. Okay, so and then let's just extract some statistical summary using the shapefile and the raster dataset that we have. Okay, so the stat that we are going to run is mean. We want to get mean for the variable, the raster dataset that we have for each of the zone for the shapefile. You've seen the shapefile on the OpenStreetMap. You remember? So we had like polygon all over. So what it does for each of the polygon, it will calculate mean. That's what we are trying to do. Does that make sense? So for each polygon we have, it will calculate mean for each of the raster dataset. So you will run through them, and then this polygon, and then we have a stack of raster, and then it calculate mean for each of them. Yeah. So so the way that zonal stat or any stat between the zone and raster works is like that. So let's say you have this raster data set. Okay. So each of this grid, you have a value, okay? 1, 2, continuous variable, okay? So now I have a shapefile or a raster, which I call it as a zone, okay? So the way that it works, so the R or GIS software will basically just overlay, let's say, the polygon geographically. It will come and be like this. Okay. So what it does, it will basically summarize all the pixel in this area. Are you calculating mean? And then it will basically calculate mean in this polygon, in this all this grid that is covered by this polygon. Okay. If you want to sum, you specify I want sum. If you want standard deviation, you say STD. You know, each of them has a function. But you have to also understand, if you want to go more in detail, how, for example, it works here, because the line of the polygon, it doesn't cover the entire pixel. Some of them have, some of them small. Some of them, you know, it's proportional. So all the GIS software, I am not entirely sure, but I think R as well, by default, it works on the centroid. So if this boundary, like the centroid of this pixel, is here, okay? So this is the centroid. It's not very sophisticated, the way that they have designed the zonal stat. What it does, only the pixel that is basically covered, the centroid of the pixel that is included in the polygon, will be accounted in that zone. Okay, but we will have 3EA tool at the end, at the last day. It does similar kind of zonal stat, but we are not using this technique. We have developed a new techniques which basically uses the proportion. What is the proportion of that coverage? It doesn't rely on the centroid, but all the GIS software, and I think are as well, by default, they work on centroid. If centroid is covered, it will take that value. If centroid is not, it will leave that pixel outside. So it doesn't basically include this two, include all of this. Not this one, yes. Not this one. Does that make sense? Yeah, so that's how the zone and statistical summary works. Any question? Okay, so let's go to the next step. So we have another functions in R. So if you want to basically, it's not really essential, but if you want to run something and you want to know how long does it take, then we have a function which we call it TikTok. It's not TikTok that we're using as an app. So yeah, don't record any video. It's not designed for that, but it's called TikTok. So at the beginning, when you run something, you activate the function tick, and then you basically include the line for running, and then at the end you say talk, and then it will give you a time, how long does it take. So let's TikTok. So yeah, we can run the first line, which is the tick with double bracket, and then we would like to calculate mean. So the line that we have, the function that could basically extract this value based on this polygon. We have that function in the line, which is extract exact extract. So that is the function, and then you basically follow the directory, and then you basically specify the raster data set that you have. We have already created a variable for it, and then we have a shapefile that we have already read, and then we have the function, the summary, sorry, the statistical variable, which is mean, we want to calculate. So click, run this line as well. And then you click the talk. Ah. Ooh.
Oh, it's there, I think. Just move so it, no, it moved the actual extensive.
Yeah, I didn't delete it, I think. Yeah, so you see, it basically finished the process and gives you the time. How long did it take? It's magic, isn't it? So, yeah, so now we have basically calculated the mean for each of the zone that we have, which represent the polygon in the shapefile. So now I would like to create new names for the variable that I have created, because I have 4 raster. They are stacked together. So this raster that I have here, I have 4 of this. 1, 2, 3, 4, all together, stacked together. And I have one shapefile which has different zone. So it basically calculates mean for each of the zone. Okay, and for each zone, I have 4 value because I have 4 raster. Does that make sense? Okay. So let's just extract the variable names. So we are creating names for our variable, which is based on the raster dataset that we have. And then if I run it, it will show you the new name, which is the mean for each of the variable, for each of the raster dataset that we have. Okay, but we want to make it more simple. So we don't want to basically have that kind of long name. You can keep it if you want, but we will just basically convert it from that long name to just X, 1, 2, 3, 4. So, but you need to always, we created some a syntax which basically save the name and the new name as well for you to be able to remember. Because from now on, we are not calling the long name, which is, we were just saying X1, which is one variable, X2, X3, X4. So to make sure that they are matching together, so we have to basically use an other kind of syntax in your script. So what it does, it will basically just extract the new names and then matches with the new variable name that you are creating. So we want a variable name with X from 1 to 4. So that's what it says here. And then replace with the names that we have before. So here we have 4. So we want to basically replace it to X1, X2, X3, X4, just to make it simple. So we just run. And then we extract new name for the raster. And then if you run it again, and then you will see that our new name for our variable is not anymore the long name mean XYZ, is X1, X2, X3, X4. So we have also a function which is called cbind. So we can basically just combine the data set that the names that we have produced. So if you run it, sorry, we don't have much time left, so I'm just trying to be able to run all of them. But it's very simple. Please, when you have time, just redo the process step by step and understand. And it's very easy to follow. So I've just created the new name for the covariate, and I would like to create a CSV file which basically save the old name, the long name, and then with the new variable X1, 2, 3, 4. And I will save it for me to be able to remember. I can always go back and look at it if I forget what X1 mean, X2 mean. So you can just click run. And then now you have saved the CSV file in the output folder with this name. So we can go back to day 2 output, and you can see we have a CSV file. You can double click and you can see we have the old names. So we have 4 old name, and we have X1, 2, 3, 4, the new name for it as well. So this is something that you save it, and then if you forget what X1 mean, you can go back to it. Okay, so you can close the CSV. So now I would like to extract the building count. So you can just follow the script one by one. Most of the functionalities I've already mentioned what each of them does. So you click on the R1, reads the building count, covariate, and then this, the second line, which basically extract the building count, but it will sum the building numbers in each zone. So you click, and then you basically merge all of them together. And then if you want to see the output, you can see. So always head, it gives you just the first part of your data set that you're producing, and it gives you the data. So what we have EAID, we have population, we have building count, and all these 4 variables that we have created. So basically the shapefile goes through all of those raster data set and summarize them based on each zone. Really? Okay, so you can run. Yeah, you can write the data, the output that we have just created as a shapefile. So that's a function that you can learn as well. Sorry, we don't have much time, so I'm just going through one by one. Then you can basically create a data frame from the data that you have. And you can apply specific like functions, let's say to convert the shapefile to data frame. And then you can basically write the final output as a CSV in the output folder with the name popdata.csv. And that's just a few simple operations for applying some covariate, creating covariate, or stacking and calling raster shapefile, doing some kind of summarization on some mean, stuff like that. There are a lot of other operations that you can do. You can always look for it online, and there are already a lot of help and scripts that you can use it. Anyone has any question? Okay. Do we have time to go through the selection?
Let me quickly rush through it. Hola. Yeah, so we have some few time before we go for lunch, but I just want us to finish with the last part, then we can go for lunch. Is that okay? Or we are all hungry? Because when we come back, we have a lot to cover. Are we okay? Right, so yes. So what my colleague has walked you through is how we prepare our data set for the population modeling, right? So these are some of the things we do from the beginning up until the end. Now, the second part has to do with a regression model. So when you have, so in terms of population modeling, sometimes we have like 50 covariates, right? And we need to select which of these covariates kind of predicts our population density, right? Because if you have 50 covariates, there is the issue of multicollinearity. Some of the variables would be redundant, right? They are basically doing the same thing. Please, how many of you are statistician here? I hope I'm not. How many of you are statistician or you have some statistical background? And how many of you don't like statistics? Okay. Okay, so for those of you who have some basic knowledge, I'll come down so that we all learn, right? I know it can be very challenging when it comes to some statistics, but it's good we all learn. So what I'm saying is that in our population modeling, sometimes we have so many variables that we need to deal with. So we need to drop some of them which are not useful. They don't predict population, right? And that is what we do. So the first thing we do here is that we are selecting, so we have a data frame that contains our covariates, right? Our independent variables. We are going to talk more statistics after our lunch, right? So we select those covariates using this line here. So run that particular line. When you run, and you click on that, you see that it has selected only the 4 covariates we want to deal with. And one of the things we do in statistics is that sometimes our covariates may be on different measurements, right? They may be on different scale. So what we do is that we can transform them so that they can all be on the same scale. And here we are using what is called a z-score transformation. So what a z-score transformation does is that for each variable, we subtract the mean from that particular variable, and then we divide by the standard deviation, right? So that is a z-score transformation. So you can see that most of the values here are very different. Some, for example, here is like 0, 0, right? So we are transforming them to a z-score so that they can all be on the same scale. So one thing about R is that you can write your own function, right? Even though R has inbuilt functions as well as the packages having their own function, you can also write your own function to do whatever you want it to do. So here we wrote a small function called scaling function, where we say that for each variable, subtract the mean of that particular variable from each observation, and then divide by the standard deviation. And in doing so, we don't include NA values because some of the observations have NA values in them, right? So you run that function, and then we apply the function to scale the covariate. So now you can see that now our values have been scaled. Some are negative, some are positive, right? But now they are all on the same unit or on the same scale. So that is a z-score transformation. When we come back, when we are doing regression, I would explain more. Then we select our response variable. So here we are selecting our population and then our building count. So how many of you know the formula for measuring population density? How do you calculate population density? Yeah, so So population density, pop density is given by the number of people, which is our population, divided by our area. In the bottom-up model, what we model is this population density here. But now we know in our data set, we have our population. And then our area, it could be buildings because we want to model people per buildings. We know our buildings. So we just divide population by the number of buildings or by the area. And then we get our population density. So that is what I'm trying to do here. Selecting population and building. Then I would divide the population by the building, but I do a log transformation, and I'll explain more when we come back. The reason why we are doing a log transformation in that particular place is that in our population modeling that we are going to do, we assume that population density is log normally distributed, which means it is positive, right? So because it is positively skewed, then we do a log transformation here so that we get all positive figures, right? We'll go into details when we are doing the population modeling, but this is just the reason why we are log transforming the value. So we will run this one. Okay, so now we have run data line. We have our response, which is our outcome variable. We have our covariate, which have been scaled. Now, what we want to do is to select which of these predict covariates, X1 up to X4, kind of is more related to population density. And there are many ways of doing it, but one of the ways we use here is called a stepwise regression. So stepwise regression is we dump all the values into the regression model, and then we ask the model to select which one predicts population density. But what it does is that it will first add all the values, remove the redundant one, or it will just start with the first one, see if it's related to population density. If yes, it will add the second one. If no, it will remove it. If yes, it will add a third one. So it's going back and forth. That is what the model is doing. So in the end, it will select the best covariates that predict population density, right? So there is a package called OLSRR, which you installed. So we just load that package and use it for it. So here we are modeling the response as a function of the covariate. So because of our time, I will rush quickly. And if you want to see the summary of the regression that you did, you use summary model 1, and you see the results, right? So, excuse me. So that is the results of our regression equation. We will come back to it when we come back. Now we want to perform the stepwise regression to see which of the covariate influences our population density. So you run that particular line and you see that it has given you some results. So based on the covariate, it says that the best covariate that influences our population density are these 3 covariates, which is X4. I think X4 is nighttime light. X2 is distance to conflict location. And X1, which is our building maximum distance. So it has selected these 3 covariates as the top 3. So assuming you have 100 of variables, Then we do this and it will select the best one that we need to use so that we don't waste our time running all the covariates to predict population density. There is also another package, Carrot. I think some of you might have it. So you can either install it, but I think you have already installed it. So let's read it in with the library function. And this is also another way. This is a machine learning way of selecting our covariate. How many of you have heard of machine learning before? I mean, the statistician, yeah. So this is a machine ridge lasso or ridge regression. It's a machine learning model for extracting our covariate, selecting the best one. So when you run that, it will also select the best predictors that predict population density. So we will quickly run it. Okay, so this is the most important chart. So here, it is showing the contribution of each of the covariates in predicting population density. So just like the first one, we have X4, which says X4 is predicting population density. We have almost, I think, around 100%. We have X1, which is around 60%, and X2, which is 60%. Then S3 is contributing nothing. So this is also another way of selecting. If you have a large number of covariates, you just select them to analyze population density. So that is a quick one. When we come back, we will look at regression into more details. Have I confused you guys? Confusing, right? Yeah, so it's because of our time. That's why I'm quickly rushing through so that we can go and eat and come. When we come back from our lunch, we are going to look at the basis of regression, and then we will do some regression models so that we understand how regression models work. See? Any questions? Any questions? Okay, so I guess we will stop here. Then when we come back, we will continue, right?
You're complete now.
Okay.
You need the mic? Que le apaga turn off the mic. Mute it. No. Mute it in the Zoom. Mute Zoom.
Hello. Hola. Yeah. Can we start? Are we ready? So now that we've had some lunch, we are going to crunch some numbers. We are going to look at some basis of statistics, right? So we will start off by defining what is a regression. Are we all set? What is a regression? So when we say a regression, it's a statistical technique that we can use to explore the relationship between what is called a dependent variable and one or more independent variable. I will explain what a dependent variable is and what an independent variable is. So assuming you want to find relationship between, let's say, poverty and unemployment, we have two variables. The poverty can be your dependent variable, right? And we want to find its association with unemployment. If someone loses his job or is not working, what is the relationship with that person in terms of falling into poverty? And so with this basic example, we can use a regression analysis to analyze the effect of unemployment on poverty. So one of the things that regression do is to model association or relationship between two or more variables that we are interested in. See, right? We can also use it to predict the value of a dependent variable based on values of the independent variable. So assuming we have unemployment, we know unemployment, and then we want to know whether unemployment can predict poverty. If we have unemployment, then we can use it to predict poverty rate for a given person or for a given observation. So one regression is used to establish a relationship between variables. The second thing is that we can use that relationship to predict new values if we have values for the independent variable, right? So I have here some examples. What is the relationship between rainfall and crop yield? We know that the amount of rainfall you will receive in an area has an effect on the crop yield within that particular area. So there's some kind of relationship. So if we want to find the crop yield total, we can know the rainfall amount, then we can model that relationship. Then we can also look at the relationship between unemployment and poverty, as I have said. So we use regression for so many things, right? And some of them, I've listed them here to look at relationship between variables, which is the dependent versus the independent variable. We can also have a cause and effect model. If you have a longitudinal data, then you can model whether something is resulting in another thing. That is a cause and effect model. We use it for population modeling, right? So we are going to learn how you use it for population modeling. You can use it for health studies. So anything you can think about, so long as you have numbers for that particular thing, you can look at that relationship. And that is what we use regression for. Okay, so within the framework of regression, we have so many regression types available. You know, I have just listed. Oh. Yes, so we have so many types of regression, and these are some of the regressions that people use. This is not exhaustive. There are so many of them that you can use depending on the variable that you are looking at. So, for example, logistic regression here, when you have an outcome that is binary, which is yes and no, we use what is called a logistic regression to model, to do the regression. For geographers, they use one of the models being geostatistics, where we predict across a surface. We have Bayesian statistics, which we're going to look at tomorrow, and so forth. So generalized linear models and a whole lot of models that we can use depending on what we want to look at. So in regression analysis, one of the things that we sometimes want to find out is whether there's a correlation, whether there's an association between two variables, for example. And one of the graphs that we can use to look at that relationship is called a scatter plot. So here we have examples of scatter plots. We have our dependent variable, which is also called an outcome variable on our y-axis. Then on our x-axis, we have our independent variable. And then we want to look at the relationship or correlation between these two variables. So we plot them on a scatter plot, and then we can see a pattern. So the pattern will tell us whether there is a linear relationship, there's an inverse relationship, or there's no correlation at all, right? So here, in this particular graph, we see a positive correlation. So as the dependent variable increases, we see a corresponding increase in the dependent variable, right? So the two values are increasing together. When that happens, we say there's a positive correlation between the two variables that you are looking at. So for example, poverty and unemployment has a linear relationship, because when unemployment goes up, poverty too also go up. So there's a linear relationship, right? So poverty and unemployment will exhibit this kind of relationship, a linear relationship, positive correlation. We can also have a negative correlation, right? An inverse relationship, where when one value is going up, the other one is coming down, right? So there's an inverse relationship. I'm trying to think of a circumstance where one value goes up, the other one will come down. Can anybody suggest something? Two things where one goes up and one comes down. Any idea? Exactly. So she is talking about fertility rate and education, right? the higher someone is educated, then the less likely they will give birth to more children. So fertility rates will drop, right? So fertility rates and education is a good example of an inverse relationship. And sometimes too, you can plot your graph and there's no relationship, there's no apparent pattern within your data set. And that becomes what is called no correlation, right? So in regression analysis, we will often see one of these things when we do our regression analysis. Okay, so in our regression analysis, I've been talking about dependent variable and our independent variable. The variable that you are looking at is called the dependent variable. And the dependent variable has other names. You can either call it the response variable, dependent variable, or outcome variable. Some people call it target variable. So if you are looking at the effect of unemployment on poverty, you are looking at poverty being your dependent variable because that's what is of interest to you, right? So poverty is your dependent variable. Then the other values that influences the dependent variable is called the independent variable. And the independent variable has other names. We have it being explanatory variable, independent variable, or often covariates when you are dealing with continuous variables, right? So unemployment influencing poverty, unemployment becomes our independent variable. See? Is that clear? Or is it confusing? Are we okay? Right. So here we are saying that our value y, which is our dependent variable, depends on our independent variables. It's been influenced by our independent variable. And usually in statistical notation, we represent the dependent variable with y, and the independent variables, you represent it with x, usually in terms of writing statistical formulas or notations. So the goal of regression, some of the goals I've listed here, is to find the relationship between y and x, or to find the influence of x on y. How does x influences our y, which is our dependent variable? Or sometimes we want to find out which of the x's best predict y. So assuming you have a large number of independent variable, you have unemployment, you have education, you have economic status, right? These are independent variables that can influence poverty. So then we want to find out among these three independent variables, which one best predicts poverty, right? So we have three variables, which one best predict poverty? And that is one of the things regression analysis also does, right? And then when we have it, we can also use it to predict future values of y using new values of x. So assuming that we do a new sample, we do a new study, and then we have new unemployment values. Then based on the new unemployment values and our previous analysis that we did, we can use our new unemployment values to then predict poverty. That is also one thing that we can do with regression analysis, right? So the most important thing is to establish a relationship between your dependent variable and your independent variable, and how that the relationship plays out depending on the variable or the parameter that you are looking at. Okay, so let's do a quick exercise. The question here is to identify the dependent and the independent variables in the following sentence. And this is the sentence. A researcher investigates the effect of housing costs on the population distribution of a city. So we have housing costs being one of them, being one of the variables. We have population distribution being one of the variables. So which one is our dependent variable? Which one is our independent variable? Anyone? A quick exercise, anyone? Independent variable. Is independent. So here, we want to find out the effect of population on housing costs. Assuming you are living in Panama City, the more people they have in Panama City, the higher the housing costs will go, right? Is that right? Because the more population you have in an area, there is a higher demand for housing. And obviously, the price of housing will go up. So housing becomes our dependent variable and population becomes our independent variable, right? So yeah, here we are looking at the effect of population on housing. So the more people you have, population becomes our independent variable, our covariate, and we are using population to predict housing. So housing cost becomes our dependent variable. Yeah, I lost connectivity. Is there any question? Do we understand what's, or it's a bit all over the place? It's part if you can let them.
No? ¿Se lo puede ver?
Wait. There we go, we're back.
Sure. Uh-huh. So we don't change it with the presentation from the one
No,
earlier.
it's the same.
We can maybe put it in these slides and then give me the 1 second. And then you can click from here.
Yeah.
But I don't know. Can you show me the edit? Well, es el puntero. El puntero para saber dónde está. ¿Veis el hielo? Oh. Like soup?
Yes, like so.
Would you like to do? No.
What's the problem? My internet's going. Why do you need your contract? I was going to I have similar points. That's what I was going to visit or Italians.
Back on again.
Okay, so we are back online. We needed a short commercial break to digest whatever I was saying. So when you are looking at a regression analysis where you have only two variables, you have the outcome variable and the covariate, it becomes what is called a simple linear regression because you have only two variables that you are looking at in the regression model. Right. So, like I was saying, when you have only two variables that you are looking at in the regression model, that becomes a simple linear regression. And this is the formula for a simple linear regression. I've tried to make it more concise. So your response is also the same as the dependent variable or your outcome variable. And we are saying that our response variable or our dependent variable is a function of one covariate plus some noise within our data set. So there's an error. When you do a regression analysis, there's an error which we cannot explain when we fit a model, and that becomes is part of our model. So we are saying that we have a dependent variable, which is a function of one covariate as well as some error, which we cannot explain. And this is the basic function of a simple linear regression. So for example, we want to model the effect of nighttime light on population density. So we are saying that population density, the number of people within an area, depends on the nighttime light that we observe. So when you take a city like Panama, for example, because we have a large number of people here. During the night, we have a lot of light reflecting back into space because more people are living here. So if, for example, you are looking at a satellite imagery, you will see more light coming from Panama City because why? We have more people living within Panama City. Compare that to maybe a rural area where less people live there, the intensity of the light will be very low because less people live in those areas. So this is an example of a simple linear regression where population density is a function of nighttime light plus this error, which we cannot explain. We don't know why we have that particular error. Then when you have two or more covariates explaining the outcome variable, then we have what is called a multiple linear regression. So here we have our response being also a dependent variable, and we are saying that our dependent variable is a function of the first covariate, a function of the second covariate, and so many other covariates, plus some kind of error which we cannot explain of. So, for example, our population density, we can say, is a function of the nighttime light that an area receives, plus maybe distance to marketplaces, then plus some error. So that's an example of multiple linear regression. So simple linear regression, we are only looking at two variables, our dependent and our independent variable. Multiple linear regression, you have one dependent variable, then you have more than two independent variables. Are we okay? Right. So it's just the name. They are all doing the same thing, it's just the name that kind of changes. Sometimes when you are looking at the relationship between two variables, sometimes the relationship is not direct, right? It's not straightforward. So this scatter plot that you are seeing here is showing that the relationship between our dependent variable, and your independent variable here is not linear. It looks like a curve, a spline, right? Or it's kind of inverse relationship, as you are seeing here. So sometimes when that happens, if you want to establish a linear relationship between the two variables, there are different ways of transforming our data set so that we can see some kind of linear relationship between the two variables that we are looking at. So there are a whole lot of data transformations available. One of them is that you can log transform your dependent variable. When you log transform your dependent variable, it has a linear relationship with the covariate that you are looking at. You can also do square root transformation. You can also have exponential transformation. So when you transform your dependent variable so that it can have a linear relationship with the covariate that you are looking at. So here, this is just a graphical representation. We have nonlinear relationship, which looks like a spline. Then when we transform it, we get something like this, right? In the previous work that we were doing, if you watch your script, there's a place where I do log population divided by building count. In the previous script that you were doing at the later part, that was a log transformation that I was doing to establish a linear relationship between population density and the covariate that we want to look at, right? Okay, sometimes too, the covariate or your independent variables will be on different scales. And so when that happens too, we need to ensure that all the covariates are on the same scale. So in doing so, we need to scale our covariate to ensure that the covariate that we are using or the independent variable that we are using is on the same scale. Then we can use it for the analysis. So for example, income is measured in thousands, right? Poverty rate might be measured in percentage. Income has like a higher number of values. Poverty rate, which may be measured in percentage, may go from 1 to 100. So we can see that the two values, you cannot really compare them because they are on different measurement scale. So when that happens, we do what is called scaling, where we scale them using what is called a z-score, so that they are all on the same scale so that we can compare the two variables that we are looking at. So that is scaling. And I did, that's the later part of the script. I did scaling, but because of time, I quickly ran through it. So there are different forms of scaling that you can use, but the commonest one is centering, and the other one is z-score. So with centering, you subtract, you find, assuming you have two variables. So assuming we have two independent variables, x1 and then x2, and they have different observations, maybe 2, 3, 4, 5, 6, 7. With centering, what we do is we find the mean of this x, and then for each observation, we subtract the mean from that particular observation. So what is the mean of these numbers? It's 2 plus 3 plus 4 divided by 1, 2, 3. What would it give us? 3. So the mean is 3. So if we want to center the x1, x value here, it is 2 minus 3, which will give us -1. We do it for 3, 3 minus 3, which is 0. This is 4 minus 3, which is 1. So we've centered the x1. That is centering. Clear? Then we have z-score transformation. The z-score transformation is given by the formula z given by x bar minus, no, given by the so the z-score is given by the formula, the value or the observation that you are looking at, okay, minus okay, so the second one, the z-score, is given by the formula, the value, which is the observation you are looking at, minus the mean. This is how we represent mean with statistical notation, divided by the standard deviation. So you use this formula to scale all the covariates like we were doing in the previous one. That is z-score transformation. So when you do that, all the variables you are looking at will be on the same scale so that you can compare each of the variables that you want to use in the analysis. All right. And one thing about statistics is that anytime we do a regression analysis, we need to measure the uncertainty associated with our parameter of interest. So in statistics, there's a term called parameter. Any unobservable quantity that you want to estimate in your regression model is called a parameter, right? So when we do a regression analysis, we want to see how confident we are in the predicted values that we have predicted. And so sometimes we may be very confident, so we will have a narrow confidence bound between our observed and also our predicted value. And sometimes the uncertainty may often be wide. So in statistics, we use what is called a 95% confidence interval to see where the uncertainty associated with our parameter of interest. And the reason for the 95 confidence interval is that your distribution, the distribution of your data set, in 95% of the data set will fall within 2 standard deviation from the mean. So we use 95%. That is the normal thing that we do in terms of statistical analysis. In Bayesian language, the 95% confidence interval is called credible interval, right? So that is Bayesian. We are going to look at Bayesian tomorrow. We can also assess how good our prediction is using what is called model fit. So statistical models can be judged by the fit, how close are the predicted value from the observed value, right? There are a number of metrics that we use to measure the statistical fit within our data set. There are a lot of them. One of them is what is called AIC. And AIC, the full name is Akaike Information Criterion, right? So when you have fitted, let's say 5 models, and you want to see out of these 5 models, which one is giving best prediction, you can look at their AIC value. The one with the lowest AIC value is always the best model, right? So that is AIC for you. We can also do what is called cross-validation, right? I think. So cross-validation is a generic name for assessing how well a model performs on data that have not been used to fit the model. And we have different forms of cross-validation. One of them is leave one out cross-validation. So this is how cross-validation works. Assuming you have 100 observations, right, with different variables in that data set, and then you want to model some regression with the variables, what we do is that we divide our data set into 2. One is used to fit the model, right? It's usually 80% or 70% of the data set which is used to fit the model. So if we have 100 observations, we will use 80% of the data to fit our model, right, to train our model. Then when we get our regression results, we will then use the 20 data point to then predict, to see how good our model is predicting the 20% that we didn't use in fitting the model. So that is a form of cross-validation. So we have leave one out cross-validation being one method. This is where if we have 100 data points, we leave one out, then use the 99 to fit the model. Then based on the 99, we predict the value of the one that we left out of the model. And that becomes leave one out cross-validation. You can also have training and test data, which is what I was describing. where we partition our data set into two. One is used to train or to fit the model. Then we make predictions on the test data and see how good they are. Then we have k-fold cross-validation, where we divide our data set into folds. Usually they use 10 folds. Then we leave the first fold out, then use the remaining fold to predict the one that we've left out. That is k-fold cross-validation. So you can do whatever you want to do. It's a way of assessing how good your predictions are. How do they explain the thing that you are looking at? So here is an example of training and the test data, where here we use 75% of the data that we had to train our model, and then use 25% of the data to make a prediction. And then we can compare what is the correlation between our observed and our predicted value. So here is showing that this is a correlation coefficient, usually represented by R. It's showing there is a low correlation between our predicted and our observed value, roughly around 40%. So it's not really that great. Sometimes too, you may have outliers when you do your cross validation. All right, so any questions so far? Am I going fast or is it confusing? No question? So we all know statistics now, right? Okay, so yeah, don't worry, we'll be doing tutorial after this PowerPoint presentation. Then as we do the tutorial, I'll be explaining more what the models are doing, so that at least you fitted your first regression. And so when someone asks you, do you know regression? You can tell the person, I have done regression and I know what it is, right? So there are some assumptions when it comes to a linear regression. One of them is that your dependent variable or the outcome variable should be normally distributed, right? And when we say normal distribution, it looks like this. It has a bell-shaped curve. And that is an example of a normal distribution. But in reality, it's very hard to find a data which will have that particular bell-curved shape, right? In reality, it doesn't really happen. So one of the assumptions is that your data set should be normally distributed. And here are examples of data sets that may have normal distribution. The first one being the height of 1,000 randomly selected year 11 school children. So when you select 1,000 school children with the age of 11 years, and you measure their height, right? And you plot their height using a histogram, it's likely that their height will have a normal distribution, right? That is an example. Body mass index, your BMI, which measures whether you are overweight or obese, will also be normally distributed. Most continuous data sets, some, not all, will also have this bell-curved shape. So bell-curved shape. We also have some data sets which are not normally distributed, and one of them is count data. So the number of people in this particular room is an example of count, because we can count everyone in this particular room. And that particular data will not be normally distributed. And when you have count of people, we use another form of regression called Poisson regression to model that particular count data set that we are looking at. Sometimes too, you may have a data which is binary, yes or no. Sometimes you go out, you do a survey, and then you ask people, do you know statistics? Or have you used statistics before? And the answer in the survey is yes, C, or no, right? So that particular kind of data is an example of binary data. And when you have binary data, we model binary data using logistic regression, right? You can also have rate or proportional data. For example, the rate of disease infection, and some other data sets which are also very skewed. So this is just an introduction to regression. We are going to zoom in into the actual exercise. Any question? So I'll be explaining more whilst we do the tutorial. Any question? So I think this is where I will need mine. Let me try. Yeah.
One moment. Sorry.
So in your day 2 folder, you will see a regression script called regression_model. Please open that particular script. So no question on regression. We understand everything. So the logic is, if you have 100 observation, right? You leave one out, which is, so you have 99. Yeah, you fit the data set on the 99, and then we try to predict the value of the one that we've left out. So the algorithm would be leaving one out for each of the observation between iteration until it finishes. That is leave one out, cross validation. So the logic is to assess how well our predicted value are to the observed value.
Yeah, but at the beginning you are trying to assess a new observation, and I don't understand exactly.
Do you want to ask it in Spanish? Then maybe they can translate. So this is more of a machine learning model where we are trying to predict the value of something. So, you know, regression, we can do inference, looking at association. We can also do prediction with our regression.
Yeah, I understand that. But you are trying to assess a data that doesn't belong at the beginning to the data set.
Yeah. So
We do that when you suppose that where your estimate belongs to the beginning. Yeah, no.
Pues creo que se está ahí resolviendo la duda. Acuérdense lo que toca hacer con los libraries, de los paquetes, ¿sí? Correr la library. Si no corre, toca instalar el paquete. ¿Ok? Acuérdense.
So the reason why we do that, they have metrics to measure our observed value. So your observed, the predicted value that you make should be close to your observed value.
Las tres líneas primeras de la librería.
When you leave one out, and you make a prediction, and you do it for all the data points, you want to see whether our predicted value for is close to the
Two
measures are close
close, how close they are to measure the goodness of it, and their metrics to assess that. In the tutorial, we will look at that and I'll explain further.
Measures like accuracy and
Measures what?
accuracy.
Accuracy. Okay, have we all opened our tutorial? Sweet. So you already have the tidyverse package installed, so we don't need to install it. We need to install the mass package, which is used for linear regression. And then we need to install another package called WorldPop, which is used for looking at correlation between two or more variables. So the way you do
They know already.
yes, so we have learned some basis of R and how to install package. So all of you should install the mass package and the WorldPop package, right? We all know how to install packages, right? See?
Sí, señor.
So let us try and install those two packages. You already have the tidyverse package, so you don't need to install it. Is it installing? See? How many people have not been able to install it? So can we progress? Okay, so if you've installed all the packages, just read the packages in, read the tidyverse, read the mass, and also the WorldPop. Just run them. So I'm running mine from here. Run. And then I've also run my WorldPop package. Okay. So in our first regression exercise, we simulate random numbers, right? And use those random numbers to do the analysis. That is the first regression exercise. And to simulate random numbers, you need to always set what is called a seed. So this number you are seeing here is called a seed number. And the reason for that number is that if we put that particular number there, anytime we simulate any observation using R, we will get the same number, right? If you don't set the seed, anytime you do the simulation, which we are going to do, you'll get different numbers. So for example, let's try it out. Let's run the seed and then run this particular. Okay. So let's run the seed, and then we are simulating from a normal distribution, a log normal distribution. Actually, we want to ensure that all our values are positive, right? Because sometimes when you simulate from a normal distribution, you may have negative values. But we want to ensure that all the values that we are simulating from are positive. So we are using what is called a log normal distribution. So we are simulating only positive values. So run this particular line, run this up to 5. Have we run that? We are doing some simulating just random numbers. Then we are simulating 2 dependent variables. One of them is a continuous value, which is the first one, which we simulate from a normal distribution. And we are, with this particular function, ABS, is to ensure that the values that we simulate are all positive, right? Because if we don't bring this ABS here, it can give us some negative values. So this ABS is to ensure positive values. The second dependent variable is being simulated from a Poisson distribution. So we are simulating count observations. Then after we've simulated our data set, we combine them all into one to have a data frame. So here we are combining our data set into a data frame. All right. So now let's see our simulated data. Let's see the structure, how it looks like. So I think, okay, sure. So we are looking at the first 6 observations within the data set that we've simulated. So just take note, our first Y1, is a continuous variable, right? Y2, which we simulated count data, is an integer. Then we have X1, which is continuous, X2, X3, X4, X5. They are all continuous variable. Just take note of the values. So the first, let me write it somewhere. So Y1, the first value is 0.49.
41.
41.
739.
It's okay. Then Y2,
1.12, 759.
Y2 is 4, right?
Sorry? Oh, sorry for
Yeah,
sorry.
X1 equals
2.05.
2.053.
3.
So here I want to demonstrate why we need to set the seed. So first we set the seed, then we simulated some numbers. Now we are going to remove that seed. And when we remove that seed and we simulate some numbers, we will get a completely new values than what we have now. So we are just demonstrating why it's important that if you are doing a simulation state, you're simulating any destiny, you need to set the seed. So comment the seed out for me. Up. So use hashtag like what Natalia is doing to comment the seed. And let's restart our R. So go to session.
Sorry.
So we are restarting our R again. Are we all following? Are we following? So now let's run our tidyverse. Let's run the mass package. We run the core plot. Then we are simulating new values.
Shall I go up the next one?
Yeah. So run your script until line 26. Run your script until line 26. Okay. And let's see what each person gets when you look at the first 6 observations. So mine, because I didn't set the seed, it has simulated a whole new values for me. So my first Y is 0.5. All of us here will have different values. What can you tell me what you had for Y1, the first value? 0.4, right? Okay, he had 0.49. So because we didn't set the seed, we are all getting different value. So that's why it's important that anytime you are doing any statistical work or simulation, you set the seed, right? So we will set the seed again so that we all have the same value to do the regression. Otherwise, everybody will be getting different results, which is not ideal. Are we okay? Right. So we will restart our R again. And then this time around, we are setting the seed. We will run. You will run from here up to line 26.
Yep.
Make sure you set the seed like this. Set seed 1, 2, 3 and run. Remove the hashtag from the set seed in front of the set seed so that you get the same value like what I have here. Is that okay? No?
¿Se desconectó?
Yeah. So we have the same value. Yeah. Okay. So are we getting this value when we run line 26? Are we getting the same values? Okay. So now we are going to model the relationship between y1 and our independent variable. So this is our independent variable starting from x1, x2, x3, x4, x5. These are our independent variables. And we want to see what is the relationship between our independent variables and our y1, which is our dependent variable. So is this a simple linear regression or a multiple linear regression? I'm saying we have y1, and then we have our y1 is the dependent variable, and we have 5 independent variables, x1, x2, x3, until x5. And we want to see the effect of the independent variable, which starts with x, on our first dependent variable, which is y1. So is it an example of a simple linear regression? Are we going to use a simple linear regression or a multiple linear regression? Say again? Multiple. So, and why are you using multiple linear regression?
Estamos usando una regresión lineal múltiple para ver de esas variables independientes cuál tiene relación con esa variable dependiente. Ok, estamos viendo una regresión lineal múltiple, viendo de esas variables independientes x1, x2 a x5, cuáles de ellas tienen relación con esa variable y1.
Yeah, so like she's saying, we are using multiple linear regression because we have more than one independent variable, right? That we want to look at the relationship with y1. So that becomes a multiple linear regression. So the next thing we want to do is to plot the relationship between each of these independent variable, x1, x2, x3, until x5 on the y1. Remember, I showed you guys a scatter plot where we model the relationship, the correlation between two variables. So we are going to do the same thing using the next line in our script. Okay. So this is what is happening in our tidyverse package, specifically with the dplyr package. There is a function called pivot long. So the data that we have is in a wide format. So we want to pivot it into a more horizontal format, and we use the function called pivot long. So here we are selecting our independent variables. Because our independent variable starts from x1 to x5, we are telling R to select all the x columns here and then pivot them so they will be below each other. So let's run this line. Okay, I think we've run it here. Can you shift this way? Shift this way. Then bring this down. Sweet. Okay, so this is the data that we pivoted. Click on it, pivot data, and let's see how it looks. Right. Are we seeing this something like this? So our data was arranged in a wide format. Now we've used another function called pivot longer to make it more horizontal. So we have our x1, x2, x3, x4, x5, x1, x2, x3, and these are their values. So we've made it more horizontal, right? So more vertical, sorry, horizontal. Yeah. Okay. Now we want to have a scatter plot to see the relationship between our y1 and our x values. So we run the next line, which is create scatter plot. Run the line 43. Can you zoom in?
Yeah.
Make it big. Okay. So when you do that, we have done a scatter plot. Are we all getting this? You are lost?
Cuando piloteo la variable x que me salgan las tres, x1, x2, x5, me sale error que sale covariable.
Okay.
Ahora sí. Ah, ya, ya.
Oh, you didn't
When
load
is
the
when's the coffee break?
You didn't load this one.
This one. Okay. It's 25 minutes.
Okay. So the graph that you are seeing is Are we all okay? Are we seeing what I have on the board? So this is a scatter plot. We are using it to look at the relationship between our y1 and each of the x variable that we have, right? We are looking whether there is a relationship between the two variables. So in regression analysis, these are some of the initial analysis that you do to see whether there is a relationship before even continuing to fit a model. So here you have a relationship between y1, which is our dependent variable, and our x1, which is one of our independent variables. So how would you describe this relationship? The line is flat. It means the relationship between, there's no relationship, or there's a weaker relationship between y1 and x1. Why? Because the line, the regression line or line of best fit is flat, like almost flat. And we can see that with respect to all the variables. And the reason is that I simulated the data. It's fake data, it's not actual data. In our second regression work, you see actual relationship between the variables, right? So this is just an example. So you will still go ahead and fit a model using these variables.
Yes, sir.
Okay, so the next thing is that we want to actually look at the exact correlation between the variables that we have in our data set. And we can do that. We are going to do that using this function called COR, or correlation. So correlation examines the relationship between two variables. So the first one that we did was a scatter plot, which was more of a graph showing the pattern. But this one, we want to have a particular number that measures that particular relationship. So run line 47 and 48. Run line 50 and 51. So we are computing what is called a correlation matrix between all the independent variables. How are they associated with themselves, right? So that is what line 51 is doing. Run line 55. Right. Zoom in.
Sir.
Okay. So in doing statistics, in doing regression, one of the things you want to check is what is called correlation or multicollinearity between your independent variable. So you want to ensure that the independent variables you are going to use as predictors in your model are not correlated with themselves, right? Because when they are correlated with themselves, they are basically giving the same information. And so we need to drop the ones which are more correlated with each other, right? So you can use a correlation plot to see that relationship. So this here is a correlation plot. It's looking at the relationship between X1 and X2, X1 and X3, X1 and X4, X1 and X5, right? X1 and X1 are the same variables, so obviously they'll correlate with themselves. And the correlation matrix ranges from -1 all the way to 1. When you get closer to 1, it means the two values are correlated with each other. There's a positive correlation. So if there's a positive correlation, sometimes people use a threshold of, say, 70% correlation, depending on the work that they are doing. So when two values have a correlation above 70%, they drop one of the variables because they basically have the same information. So here we can see that our variables are not correlated with themselves, so we are good to include all of them in our analysis. The brighter colors you are seeing here, which correspond to 1, is the same variables that we are looking at. So we don't need this particular one here. What is important is these ones over here. And we can see that they are not correlating with each other. So we will do another correlation plot where it assigns actual value to the correlation between the independent variables, that we are going to use. So run line 57, run line 58. Right. So here we have an actually assigned correlation number between our independent variables, right? So when you look at it, it says that the correlation between X3 and X4 is 0.04, which is very low, right? X3 and X1 is even negative. It's an inverse relationship, which is also very low. So the same graph that I showed previously, you can also do it this way if you want to see the correlation between your independent variables. So these are just some initial things that you do if you are about to do a regression analysis to see how your variables are playing out even before you fit a model. Are you okay? So these are just graphs that you can present in your work. They are super cool, you know. When you plot some of these graphs, it shows that you know what you are doing.
If you want to impress.
So now we are actually coming to fit a model to find the relationship between our independent variable, the X values, and the Y1, which is line
73.
Oh, we are actually going to do a histogram, right? So one of the assumptions of a linear regression is that our dependent variable should be normally distributed. So we want to test this assumption using a histogram. So a histogram will plot the values and we can check whether it's bell curve, or you can also use, there are various statistics that we can use to measure a normal distribution in terms of the skewness of the data set. So we have things like skewness, we have ketosis, which you can use to measure whether your data, the dependent variable, is normally distributed. So that is what we are going to check. I'm using a histogram here because a histogram will also tell you whether your data is normally distributed or not. So we have done a histogram of our dependent variable. Have everybody done it? See? So how is the dependent variable normally distributed or not? Is it normally distributed or not?
No, really.
Is it normally distributed or not?
Half a leg distributed. Half a leg distributed.
Sí tiene la forma. Tiene la forma. Yes.
Yes, it's C. Okay, is there any other observation?
No.
So, Mr. Silvanus, right?
Silva.
Silvis is saying it's normally distributed. Any other observation?
Él dijo que sí.
So you support him, right? No, okay, okay. So your name, please. Magdalene. Magdalene disagrees with Mr. Silvanus, right? So
Who is right?
actually,
Fight.
our data is not normally distributed because a normal distribution must have a bell-curved shape. This doesn't look like a bell-curved shape, right? But we will still go ahead and fit a linear model because in actual fact, only few data sets that you have that you see a bell-curved shape. Most of the data sets that you are going to use in your regression or whatever you want to do, they are somehow skewed either to the right or to the left. Unless we transform, we can apply a log transformation to transform this data. And when we do that, it will become a bell curve shift, right? But we don't do that. We are going to use the actual observation to do the regression. So this is one of the ways of checking whether your data is normally distributed or not with a histogram. Simple as that. So we are fitting our first regression model using only one of the independent variable, which is x1. And this is how you write your model. So here we are creating an object and we are saying that it should fit a linear model. LM means linear model. And we are saying that y1 depends on x1. So there's a relationship between y1 and x1. Then you specify the data set that you are using. So you need to specify all these arguments in our linear regression model. So here we are fitting only a simple linear regression using only x1. After we finish with that, we are going to use all the variables to do a multiple linear regression. So we have just run the model here. And to see the results, you type summary and then you write the objects that you created in the function. Okay. So we fitted a simple linear regression. And then we have some results over here. This is actually the syntax that we wrote. Then we have what is called residuals. So if you remember when I was showing the linear regression formula, I said there was some errors that we cannot explain. So when you fit your regression, we measure how close our observed value are with our predicted value. So when you subtract the predicted value from the observed value, you get what is called residuals. And those residuals are the errors where we don't know, we cannot account for them in our model. So these are the residual values that you are seeing. But the most important part of any regression, especially if you are doing inference or looking at relationship, is this particular portion of our results, right? So first we have what is called an intercept, right? And then we have our X1. What this intercept means is that assuming we don't have any covariates or X1 in our model, what is the baseline value that we will get for Y1? And that becomes what is called an intercept. So it's like a baseline value within our regression model. Then we have the effect of X1 also here. So what you want to look at in every regression is the estimate here, right? Estimate here is what you want to look at. So from the model we fitted, the estimate for X1 is 0.01188, which is saying that when we are looking at the relationship between Y1 and X1, the effect of X1 on Y is 0.01188. And because this is positive, it's a positive number, you can say that there's a positive relationship between X1 and Y1. And this is how we interpret the results. We say that for every unit increase in X1, our Y1 increases by this particular number. So I'm going to write the regression equation for you. We have Y1 equals to the intercept is a baseline model. We call it alpha, right? Alpha parameter, which is the intercept, plus X1. So now we know the value of the intercept to be 0.75. 0.75. And then we know the value of X1 to be 0.011. 0.012X1, right? This is our regression equation over here. So anytime we want to predict the value of Y1, if we know the value of X1, we just multiply it by this coefficient here. It's called coefficient beta values, and we can find the value of Y. Are you okay? No? So this value here is called coefficient, right? And our coefficient explains the power of X1 in influencing Y1, right? And I'm saying that in terms of interpretation of X1, we are saying that for a unit increase in X1, the value of Y will increase by this particular number that you are seeing here. No? Any question? Any question? So we have Y1 equals the intercept 0.75 plus 0.012 x1, right? And I'm saying that this number here is what is called the coefficient or the beta values. And the interpretation of the coefficient is this, that the effect of x1 on y increases with this particular value here. So for a unit increase in x1, right, 1 unit increase in x1, the value of y1 will increase by 0.012. Right? So if someone wants to predict the value of y, assuming we have a new data set, right? And we know that for one observation, x1 is equal to 2. And we want to predict what will be the effect of this new value on y. We just need to slot this particular 2 in our regression equation, and voila, we can get the value of y. So it will be y equals 0.75 plus 0.012 multiplied by 2. So calculate this and you get a new value for y. So now we are doing a prediction. We are predicting the value of y based on a new data set. No? Am I confusing you guys? Another thing too that you need to look at is this particular area. You see the asterisk that you are seeing here. It shows the level of significance of our variable, right? So in statistics, they mostly use 95% confidence interval, which correspond to a p-value of 0.05. So when you do any analysis and your result is statistically significant, you will see an asterisk with respect to that particular parameter that you are looking at, or that particular variable you are looking at. So here, our intercept is statistically significant, but our x1 is not statistically significant. There is I don't want to go much more into statistical theory, but the p-value represents the likelihood of making a type 1 error, right? The probability of rejecting the null hypothesis when it is actually true. Okay. I think we should go on. You know, you are not going to, I mean, this is just foundations, right? We build upon knowledge. So now that you know a little bit of statistics, when you go home, you read more about it, and this is how we learn more. You are not going to get everything the first day. It's understandable, right?
Shall we go for a little break?
Okay, so
5 minutes.
Can we take some break? You want to?
Vamos a hacer una corta pausa. Una corta pausa de unos 10 minuticos para que se refresquen sus cabezas de la información que les estamos dando, se tomen un café y vuelvan, ¿ok? 10 minuticos, volvemos, ¿ok? una corta pausa. That's very good process.
Yeah.
It's a lot to absorb, but it's good.
You're explaining it well.
Huh?
You're explaining it well.
Yeah, but they are not getting it. They are not getting it.
But that's
Only
okay,
few
they are getting, yeah,
people,
that's
but-
good. And that's the important thing. A few people we get
Yeah,
it. and
nobody-
that's okay.
This is the problem with big audience.
Yeah, and then, yeah, just remind them that p-value, they're always the thing that they need to look when you're looking at it. Just what p means doesn't matter. You just look for that p. That's it. No need to go in detail. So, excellent.
They took it away. Oh. Wow. Just a short. Don't break them.
Just a short break to revenge their minds and some of them are totally lost. Like they say, no, I don't know.
Rush through quickly.
Okay. Yeah, it's what we do. Maybe they don't need to, in some cases, they don't need to understand every single bit. It's more about understanding why you need to know these. I can link it back to the population line. You need to understand those relationships.
This is a nice job to have.
But the
Yes,
translation,
translation.
maybe.
Just assemble people who are fluent and create a company.
Yeah.
Make for someone.
Except the guy, except the guy was saying in a few months, AI will. His job is no more.
Sure.
It's quite possible in a year or something you will have a software that can just listen and pretty good at translating.
It's true.
I told you so.
Por aquí. Ay, check my screen cover. Sí, I love it because in Brazil, the mannequin, they dress him up always for advertising. So last time I was there, in the morning, it was like all dressed up.
Is that legal?
Yeah, and then in the evening he comes back and be naked.
They pay money, companies to do it.
Yeah,
Seems
they
crazy.
have a
Famous landmark.
soundline. Yeah, my screen's always, and I have my travel pictures. So I don't know why. I was really gonna.
Got much left?
Yeah, a couple of, I'll rush through quickly.
I think, yeah, the important thing is that you have to understand every single line of what's going on. It's like linking it back. Okay, why are we doing? Or why are we doing regression analysis? Because I can predict population, and that's related to multiple factors. It's like don't need to understand all the code, all the reasons. This is the reason why we're teaching us.
Yeah, we have
I remember
one.
I'm doing that with Thailand. We had kind of bit on the statistics, then back to the like explaining why you're doing it. But yeah, you're kind of doing that. Yeah, it's hard. Mixed group.
Yeah, I think when it comes to the model, it's quite complicated. So you just take the live part of it and then you need to listen.
Yeah, you can they can just here's the section of code. It does this. You don't need to understand everything. If there are those that really want to understand, then we can talk in the break or something. And then just say, run the code. Here's the outputs. The map. This is what the statistics mean.
Yeah, like for example, all the correlation and stuff, just not necessary. This function can be used for correlation. You run it, it's like otherwise you get really confused yourself as well. Okay, and also something they have. Some of them are good, like they were very
it's difficult because they want to go into details.
But then like they can have a very run color.
They run everything. Sitting.
Okay. Another minute. I don't know what time I said, but
5 or 10 minutes, but soon. And when does it finish? When do people meet together?
I think 4:30. 4:30. So in half an hour.
No.
About an hour and less.
Rush.
No, this is for half an hour. 4:30. No?
But only 15 minutes.
Until when?
4:30.
No?
No. What time is it?
What time zone?
You got the wrong time
So,
zone.
It's
340. You said 430.
430.
So we put only 15, huh?
Oh, 50. Yeah, yeah.
50, I know.
Oh, yeah.
That's it.
We said 15.
Yeah, we're like something.
No, 50, sorry.
Yeah. Take the coffee.
I know that was
New coffee. Exactly this time.
But this is different than that.
Yeah, it's gonna-
We need to say that for tomorrow.
That's it. It's still like a-
Constant supply of coffee all the way. So the things in the Again, explain the way. And then you go on, I guess. There's no other thing what we're going. You know, you are more. There was one in the toilet and one in his one outside, but we can go with everyone in the front. Oh, the girl is there. This one was in the toilet and then there was someone behind me. Okay, this is come and then there's one more. Just one more. It's from Shall we move on?
Yeah.
Go for it.
Hola.
No, yeah, that's all.
Hello. Hello.
Hello. Yeah. Are we now refreshed to take more statistics?
Refresh without coffee.
So
Refreshing cafe.
the reason why we are learning the basics is that in population modeling, this is essentially what we do, right? So it's important that we know some of the basics because if you want to predict population, we are going to use regression, right? So because of our time, we are going to look at a multiple linear regression and look at the relationship between Y1 and all the variables. Right, so you run line 87 and you look at the summary of the results. So now we have all the variables here and their estimates, respective coefficient, they are called coefficients. And then you look at the p-value to see whether the p-value is statistically significant or not. And all the variables that we have run, their p-values are not statistically significant, right? And when you look at X5, it has a negative relationship with Y1. All the other ones have positive relationship with Y1. So that is a multivariate linear regression. So we've done the simple linear regression. We've done the multivariate linear regression. All right.
1 minute. Oh.
So I will jump line 94. In our data set, we have Y2, which is a count data. And so because it's a count data, we fit what is called a Poisson regression. So when you go home at your spare time, run this particular line, it's a Poisson regression. And then you will see the results of that particular analysis. So now we are going to work with an actual data set, right? The first one that we had was simulated. We just created them. And now we want to use an actual data set to see the relationship. And in the mass package, there's a data set called Boston housing data. It shows the prices of housing as well as its other variables such as, okay, let's run the data and let's see the variables in the data set. So this is the Boston data set. Run line 108. That is the Boston data set. It's already a data set in R, right? Natalia, calm down a bit.
Oh, sorry.
Okay, so if these are the variables in the data set, but we don't know what they stand for, right? So to see the meaning of these variables, we run line 119. And then it provides a description of the data set in our plot area. Okay. Up.
Oh.
Down a bit.
Sorry?
Down a bit.
Oh, sorry.
So in our data set, we have crime rates. The first one, this one, see crime rate. We have proportion of residential land zone lot over 2,500 square feet. We have proportion of non-retail. We have Charles River, which is a categorical variable. So the Boston data set contains the prices of housing as well as other variables that may influence the price of housing. So now we are looking at the effect of these variables, such as crime rate, such as the lot size on the price of a particular house in Boston, right? So we are going to do a regression analysis using that data set. So just as we did a scatter plot, we can also do a scatter plot to look at the relationship between the price of housing and the variables that we have in our data set, such as crime rate. So you can run line 124.
Hold on. Something happened on the top. I didn't read this one. Okay. Hold on a minute. Is this one? No, wait, what? I run it. And then, oh, this one?
Yeah, that one.
And then,
Got it.
Apologies. Oh my goodness.
And zoom
Okay.
in.
A massive plot. Okay. There.
Okay, so with this Boston data set, we
Need to run
see
everything.
some perfect relationship, right? This is age, this is number of Black people, this is crime rates, this is, I need to check, right? This is number of rooms, this is the tax rate. So here, in terms of the value of a house and Black people, there is a linear relationship per the Boston data set. So as the number of Black people in an area increases, the housing value also increases per the data set that we are seeing. There is a linear relationship, even though it's not a strong one. This shows a perfect linear relationship. I think this is the number of rooms. So as the number of rooms increases, the price of a house also increases. This is kind of more of a perfect relationship. Oh, sorry. The black one was an inverse relationship, not a linear relationship. So there's as the proportion of Black people increases, the price of housing goes down. And this is what we are seeing in this particular area. This one is a positive one. As the number of rooms increases, the price of housing also increases. So what we are going to do is to fit a multivariate regression with the variables that we have in the data set.
Sorry, sir. I got distracted by Sacho. Playing Sacho.
Are we all okay? Are we on line 137?
Algunos les debió haber corrido error, pero vieron si corren todas las líneas desde antes de. Sí, toca correr desde la 108, 111, 113, 116. La 119 es opcional. Y ya luego el pivot y el scatterplot.
Okay, so some of the plots that we are going to plot now, we've done it in the first regression, so I'll just run over it so you can also run through it in your workflow, right? Because of time. Okay, so this is our scatter plot. We all know what it does. Yeah. We can also do the correlation, just like we did in the first part, looking at the correlation between our independent variables. So this is our correlation plot that shows the relationship between our independent variable. And can you run the next line?
Ay, sí, señor, sí, señor. Where? This one?
Yeah.
¿Y este?
Run. Open this
Sí,
one.
ajá, sí, señor. Ay,
Okay, so this is our correlation, just like we did in the first one, looking at the correlation between our independent variables. We do the same thing here, and we can see that some of the variables are very correlated. So in doing a normal regression, we need to drop some of the covariates that are more related with each other because they are providing redundant information, which we don't need, right? So always make sure you have this plot. And usually if the correlation between two variables is, let's say, more than 90% or 0.9, then you drop one of the variables, right? But here I don't drop them. We just use everything in the analysis. So we are running the next line.
Sí, señor. En la 158.
So the next line, what we do is to fit a multivariate regression, looking at the price of housing and the other independent variables that we have, such as the proportion of Black people, the number of rooms, the lot size, and so forth. So this is what we are doing over here. This variable here, MDV, is the medium housing value for a particular observation. This is crime rate. I think this is zinc. This is distance to industrial area. I need to check this value, but this is the number of rooms. This is the age of the property, right? So we are looking at the price of a particular house based on those variables. Are those variables able to predict, or do they have a relationship with the price of a house in Boston? So we use a multiple linear regression in the work. So we run our multiple linear regression, line 158, and then we can see the results. Okay, do we all have these results? Or you are now confused? Are we all okay?
Ay, dos.
So we did a model looking at the prices of house and independent variables such as crime rates, zinc, distance to industrial area, number of rooms, the age of the property, the tax, I think this is tax ratio, the proportion of Black people. So is there a relationship between the price of a house and all these independent variables? And here we can establish that for crime rates, there is a negative association between crime rates and the price of housing because of the negative sign you see here. So this simply means that as the crime rate goes up, the price of housing decreases. And it makes sense, right? If you are living in a place where there's more crime rate, then obviously nobody wants to live there. And so the property value for that area will come down, right? So our regression model is saying that there is a negative relationship between crime rate and the price of a house. And this result is statistically significant based on the p-value, right?
And so forth. Dale. Move.
Number of rooms here, which is one of the variables, also shows a positive association with the price of a house because of this coefficient here, which is 3.85. So it simply means that as the number of rooms within a property increases, the value of that property also what? Increases, right? If you have more rooms in your house, you obviously will sell it for more money, right? You want more money out of your property. So our regression is saying that that is the case, and our result is also statistically significant. So you see, with regression, we are able to model different scenarios to look at different variables. And this is real data set, so it kind of makes sense when you are looking at the variables. So we will move on. Any question?
Let's go on.
Okay. So we are moving on to the last part of our class, and that is cross-validation. So this is more of making a prediction and then assessing the accuracy of our prediction. So if you do remember when I was presenting, I made mention of cross-validation, and one of the methods we use is to divide our data set into a test data and also a trained data set. The trained data is used to fit the model. Then we use the test data to make a prediction and see how our model is doing. Is it able to predict very well when we have a data set that has not been used to fit the model? And that is all what people who do machine learning, that's what they do, right? They make predictions based on new data sets. So they train a model and then they make a prediction. And if you remember, I said regression, you can use it to look at relationship between two or more variables, which is what we have done, or you can use it to predict the value of the dependent variable based on a new data set. And that is what we are going to look at to assess the performance of our model. See? So that is the last part. So now, I believe everybody here can do a regression analysis and explain the results of their regression analysis. At least for the basics, I know it takes time to understand some of these things, but at least we all know the basics, right? So if anybody asks you, have you done regression before? You can say, yes, I've done regression before, right? So what we are going to do is that in our Boston data set, we are going to split it into two. we are going to split it using 80%. So 80% of our data set would be used to train our model. And then we are going to use the remaining 20% to predict and see how good our predictions are. So here, right now, we are doing machine learning, supervised classification. So this is more of machine learning model. So this script here, first is partitioning the data set into two, 80% known as the test data, 20%, 80% known as the trained data, 20% known as the test data. Okay, so you can run the second line, line 170. Okay, now let's look at our test data. Okay, so I think the Boston data set, the whole data set is around 508 observation, right? Now we've partitioned it into two, right? We've splitted the data set into two, 20% for testing, 80% to fit the model. And this is our test data set. We also have our trained data set, which is 404 observation. So the total number of observation in the Boston data set is 506 when you add 404 to 102, 80, 20. Are we okay? So now we are going to fit our model using the trained data, which contains 80% of the samples. Then when we finish, we will use the 20% to make prediction to see how our predictions are doing. It should be trained. Yeah. Please, I made a mistake in my script. Here, change it to trained data, not housing data. Trained data. Right? So even if you are experiencing coding, sometimes you can make some errors. Yes, so line 175, when you get here, change it to trained data. Line 175. So type trained data here.
Algo que hace R que es interesante es si ven que yo seleccioné toda la palabra de train data y me muestra, le pone color y también le pone color en donde la encuentra en otras partes en el documento. Entonces, aquí es importante porque vamos a correr el modelo con el train data, entonces yo me aseguro que en mi modelo tenga el train data, ¿ok?
So I hope you understand what we are doing so far. We are going to measure how accurate our predictions. And to measure how accurate our predictions are, we need to split our data set. Fit on train data set with the model we train it, and then we make prediction using the test data. Then we can look at our results, right? So we run our train data, right? We fitted our regression with the trained data. Now we have what is called in-sample prediction, right? So we want to look at the accuracy of our model using the trained data set alone before we will use the test data. So this line here is doing that. It's looking at the predicted value with respect to the observed value, how different they are from each other. So line 178. And in terms of measuring how good your predictions are, we use the residuals from our model. And the residual looks at your predicted value minus your observed value. So based on the residual here, we can create different metrics that we use to measure the performance of our model. And this time around, we are measuring the performance using our trained data set only. And that is called an in-sample prediction. So the 80% data set that we use, we are looking at the performance. After that, we are going to use the 20% test data and also measure the performance. So we calculate the residual.
Does it need to have here the train or the test? The train. En la línea 178 también tenemos que cambiar en vez de HSE data, necesitamos tener train data, ¿ok? Atentos al cambio. Y acuérdense que lo podemos seleccionar y asegurarnos que es la misma que queremos hacer. Train data y train data, ¿ok? 178. Y así ya podemos correr el train evaluation.
Okay, so here we are doing in-sample prediction and we are calculating a number of metrics that we use to measure the performance of our trained data. And one of the metrics that you can use is called bias. And the bias is the mean of the residual, where residual is your predicted value minus the observed value. You can also use the mean square error, which is the mean of the residuals raised to the power 2, right? Then you have your root mean square error, which is the square root of the mean square error. Then we can look at the correlation between the predicted and the observed value. So these are some of the metrics that statisticians use to measure the performance of their model. So let's run that one and see the results. Okay, so usually the lower your bias, the lower your mean square error, the lower your root mean square error, the good your model is. The higher your correlation between the observed and the predicted, the good your model is, right? So bias should be low, mean square error should be low, root mean square error should be low, but the correlation should be high, right? When the correlated between the observed and the predicted is high, it means our model is doing very well. But in order to assess whether our model is doing well, this is just the trained data set. We need now to predict the model using the test data set. Then we can compare the results of the trained data set with the results of the test data set and see if our model is indeed doing very well or predicting right. So this is called an in-sample prediction, right? In-sample prediction has to do with making prediction using only the trained data set, that we've trained our model on. We will now make prediction using the test data set, which we didn't use in fitting our model, but we are using those values to predict the value of housing in Boston. Am I confusing you guys?
El valor no me sale, el valor no me sale igual. El de bias MS no me sale igual.
De pronto es porque te acuerdas que tú cambiaste los dos HS valores por trade.
Sí, los que me indicaron, pero era la línea.
Había que cambiar los dos. Sí, un puesto aquí, era uno más arriba. Puedes volverlo a correr acá, desde ahí hacia abajo. Dale, sí, sigue dando.
Okay, can we go ahead? Let's make prediction using our test data, and then we will compare our results to see how our model is indeed doing. So this line here, line 196, is using the model that we fitted with the trained data to make prediction on the test data set, this particular line. So here, we are not fitting a regression model. We are actually using the regression model that we fitted with the trained data set to make prediction using a new data set, right? So when I wrote this formula here, right, I said if we have a new value such as 2, then we can predict the value of y. So that is what we are doing in this particular line here. So the regression model that we created with the train, we are making a prediction with that model using our test data set. And then we will calculate the metrics again and then compare our results. So fit. Okay, calm down. Yes, so here we are evaluating how good our predictions are with the test data, right? So this time around is the test data, not the trained data set. And we calculate the same metrics that we calculated with the trained data set, such as the bias, the mean square error, absolute mean square error, the correlation. We are doing the same thing over here using the residuals. And this kind of evaluation that we are doing is called out of sample prediction. So the first one, which has to do with the trained data, is the in-sample prediction, right? This one is called out of sample prediction. So we have our results here. Now we want to compare our out of sample prediction with the results from the training data set. So we use what is called R-bind, which is row bind, and then bind them together and we can compare how our model is doing. So, yep. So now you can see this column here is our test data results. And the first one is our train. The first row is our trained data resource. So we calculated the bias for each of them. We calculated the mean square error for each of them. We calculated the root mean square error and the correlation. And in general, I said our bias should be very low. So when you look at the test data results, the bias is not that low when you compare it to the trained data, right? When you look at the mean square error, the mean square error from the test data is actually higher than the trained data set. When you look at the root mean square error, the results from the root mean square error from the test data is actually higher than the trained data set, which simply means that our model, we call it what is called overfitting. So our model is really performing bad with respect to the test data set, right? So usually to have a very good model, to see that our model is performing very well, the results from our test data should perform better when you compare it to the training data. But here we are seeing that our training data is actually performing better than our test data. So in statistics, what this is called is that our model is overfitting the data set, where our results from the test data is actually performing bad when you compare it to the trained data set. It should perform good when you compare the results of the test data. The test data results should perform better when you compare it to the trained data. But in this scenario, it is actually performing bad. So our model is not doing well. We can go back again and refit our model, train it again on new variables, or drop some of the correlated variable, and then fit the regression analysis again, do train data, do test data, and see if we will get good results. So this is kind of a machine learning process, right? So in terms of our population modeling, anytime we make prediction, anytime we fit a model, we then have to come and see whether the data set that we've trained our model on is actually doing very well. So we are still going to come back to this particular metrics when we are looking at population, modeling population, because we need to be very certain that whatever regression analysis we are doing, we are producing good results. We are not just doing anything anyhow. We want to ensure that if we say there are 10 people within this location, is it really true that there are 10 people in this location? How do we measure the accuracy of whatever model we've fitted, right? So we will come back to this tomorrow when we are looking at actual population modeling. We have 6 minutes more before we close. I hope I've not succeeded in confusing you guys. Yeah, so practice makes perfect, right? If you've not used statistics before, I'm assuming this is your first, class, and these are some of these models are more advanced, right? So when you go home, take your time, read about some of these things in the literature, practice this script again, and if you don't understand anything, just Google and see. There are a lot of information that you can find online which would explain some of these statistical concepts. Any question?
Voy a hacerlo en español. Es en español. Spanish. Ok. La verdad no sé si mi pregunta va a ser un poco tonta, no sé mucho de esto, pero ¿qué tanto podrían estar influenciados los resultados del test por la parte de training que el modelo seleccionó? Se puede ser que si se hubiese seleccionado otro 80% diferente, los resultados hubieran sido mejores. Entonces, no sé si hay otra forma mejor de hacerlo o es hacerlo muchas veces hasta que tengamos los mejores resultados.
Yeah, so that's a very, very good question and observation. So when we splitted our data sets, we use a seed, right? It's using the same seed that we made reference to at the beginning. If we should change the seed, it's going to select different samples, right? So you are likely to get a different result when you change the seed, and it will sample different data set, it will sample different training, and it will sample different test sets, right? So we can try that one quickly and see, right? If you guys have time, right? So let's change the seed, make it 4, 5, 6. So the samples you select for your training and your testing can also influence your results, but you can do it multiple times and see if you have stable results. If you have stable results where your model is not performing well, then irrespective of the samples you select, your model is still not performing well. But if when you change the seed or the seed number, and then you select new samples, which is performing best, then it has to do with the samples that you selected in making predictions for the test data set. So that's a very good question. So now we change the seed, and then we will run our analysis again and see if we will get a different results when we compare our training and our test data sets. Okay, so we have changed the seed. Now we have different results, but look at it still, our model is not doing very well. The row 2, which is the test, still has a higher value when we compare it to the train. Usually it should have a lower value when you compare it to the train to make sure that that is performing best. But we can see that our mean square error is still 24, which is higher than 21, which is our train data set. Our root mean square error is higher than the train. The test data, the correlation is even bad, right? This is 0.82 when you compare it to 0.86. So it simply means that you can change the seed again, select different samples, run your analysis and compare. And if you get some of these results, it simply means that your model is overfitting. In statistics, it's called overfitting, right? So what you need to do is to maybe drop some of the variables, right? Some of the correlated one, and use a more simpler model and see if you get good results, right? So that was a very, very good question. Any other question? All right. So tomorrow, we are going to look at Bayesian statistics. The statistics we just learned today, they are called frequency statistics. Tomorrow, we are moving to something higher. We use Bayesian statistics in our population modeling, so it's good you learn the basis of that one too, so that you can also predict population for your countries, right? So tomorrow we will start with that. Any question? All right, so it's a pleasure teaching you guys.
Please, if you haven't received a WorldPop brochure, let us know that we can give you a copy. So this has a kind of small introductions about the type of research project data set that we produce at WorldPop. Generally, of course, we have like more than 50,000 data set on our website. But this is just a small introduction to our group. So if you haven't received one, please let me know. I can pass one to you. And thank you very much for your active participations. I know that we had a lot today, but the best part is you have a lot of instruction that you can take it with you and then go and run it again on your time and understand all kind of step when you have more time. So thank you very much, and we will see you tomorrow. Have a great afternoon.